In this video, we're going to get started on a new project building a GPS-based speedometer using Arduino. Hey everyone, this is Matt with Learn Everything About Design, and in this video series, we're going to be kicking off learning Arduino, and specifically we're going to make a GPS-based speedometer. Now, if you've played around with Arduino before, then you know a bit about it. If you've played with GPS before, or if you have basically done any electronics, then you've probably heard some of these terms. But in this first part of this series, I want to talk about what Arduino is. I want to talk about some of the basic equipment that you will need. And in the next couple videos, we'll get into things like basic program structure, creating some graphics, custom functions, and so on. But before we ever get to that stage, I think it's important that we sort of level set what we need to know and where we should be at in order to tackle a project like this. So first, let's talk about what Arduino is. Now, Arduino has become a common term similar to things like saying Band-Aid or Q-tip or Kleenex. It has just become sort of ubiquitous with electronics projects. Now, Arduino has a lot of clones out there or a lot of other boards, things like the BeagleBones, there's the Microbits, Raspberry Pis, M5Stacks, and so on. I'm going to use the term Arduino simply because we're going to be using the Arduino IDE or the development environment to program our projects. It's important to note that most Arduinos, as well as most other different types of microcontrollers, can use Python, UI Flow, and various different types of languages. But we're going to focus on the Arduino language because there's a lot of resources and information out there. But first, let's talk about what Arduino is. Now, years and years ago, Arduino started as sort of this development board to help you prototype your projects. Now, the Arduinos themselves do have some limitations, and it's important to note that there are many different types of Arduinos. The one that you see most often is the Uno, and the Uno comes in lots of different kits. You can see it's $23 here in the US, and it has a lot of great power and functionality, but it's missing out on a few things. You'll notice there are other boards like the Mega, there's Nanos, there are all different kinds of boards and developments kits that you can get depending on what you're trying to do. So where something like an Arduino has a lot of benefit is that you can very easily prototype your projects. There's a lot of input and outputs, both digital and analog. There's a reset button on there. There's some LEDs and so on. What I find to be pretty helpful about the Arduino is just the support that's out there. However, I have found that other boards offer a lot more functionality and a lot more flexibility. Once you start to get past some of the basics, then you can start to figure out if something like a micro is a better choice for you. I'm also a big fan of the websites SparkFun as well as Adafruit. They make a lot of good components and boards. I've used some of the MO boards, and these are SAMD chip boards instead of the ATmega boards. And these are very powerful and very small. The Trinket MOs, the Cutie Pies, all these little boards are very small but very powerful. And you'll find that the limitations you end up running into with something like an Uno tends to be in the memory department. So once you get past just some very basics, then you start to realize that the amount of memory that you have available to perform the tasks you want requires a sort of a next level of understanding memory management and building out program structure that way. So again, I think that the Unos are great, but I think it's a great entry point. And once you start to build out your own projects, then you'll start to find that there are probably better choices for you. So now it's time to talk a little bit about the equipment that we'll need for a project like this. Now, I have done GPS projects with an Uno, actually a different version of the board that had a little bit different specs, but basically an Arduino Uno, where I used an SD shield on top of the Uno, and I wired up a GPS module. Now, this can work just fine. You can get into it for about $40. The downside to something like this is then you have difficulty having a screen to display. There are also different boards, like, I don't even know if you can still get them, but there is a micro view. And let's go ahead and just see if we can bring this up. So the MicroView was a small Arduino that had a built-in OLED screen, and the OLED screen was something like 32 pixels by 32 pixels. Now, where this was really great is because it was about the size of a watch, and you already had the screen on it. You had a limited number of input and outputs compared to just a regular Uno, but you do have the ability to have the built-in screen, which means that you can put this thing directly onto a breadboard and you can wire up a GPS module and play around with it like that. But again, that's a very small screen, very small number of pixels. You don't have a lot of flexibility there. So for my projects, what I decided to do was go with a company called M5Stack. Now, M5Stack is pretty neat. The controller inside is an ESP32 in most of them, which means that it's much faster than a lot of the Arduinos, at least the Unos, if you're talking about the entry-level parts. And it already comes with a lot of great features. Depending on which M5 you get, it may include a touchscreen. This one here has like a capacitive touch 3 buttons. The one that I'm using is a gray, which is no longer available. There are similar ones to it, but the gray actually had physical buttons on the outside, where again, some of the newer ones have these capacitive touch areas. Also, some of them have touch screens, so you can get extra functionality there. These have SD card slots in them. They'll have Wi-Fi capability and Bluetooth capability. They'll have microphones and speakers built in. And one of the great benefits of this is that it already has a battery as well, which means that it can be completely self-contained. The version that I have, the gray version, the reason I got this one is because it had a built-in 9-axis IMU, or an inertial measurement unit, which means that it had accelerometer, a magnetometer, and a gyro, which is great for doing things like acceleration and deceleration, roll, pitch, and yaw on your projects. Another great benefit of the M5 stack, just sort of the general M5 stack, is that the premise behind it is that you can remove the back and stack other modules to it. So the reason that this is important is because you can get things like extended batteries, you can add on additional functions like prototype boards, and there are different modules like these GPS modules where you can stack them on and you can have both an internal and an external GPS module. And this means that it's really easy to develop projects for things like a GPS Speedo. And again, there are some pros and cons to these. The battery life is probably going to be limited. If this is going to be going into a vehicle, then you do have a USB-C connector on them. So again, they do have batteries. You can get extended batteries. But what we're going to be doing for the project here is I actually have one of these mini GPS units. Now, these mini GPS units are great because they have these groove connectors on them, these 4-pin connectors that plug directly into the different units. So again, I'm using an M5 stack. There are other ones such as the smaller boards, which are called the sticks. There's also atoms and stamps. And as you look through here, you can see that there are these various development packages. So for example, here's an M5 stick C with watch accessories. So this is a tiny little development platform, has a screen built onto it, and it comes with the little watch band. And again, you can start developing your projects using these. It has the groove connector on it, which means that a lot of times you can directly plug in your sensors. With some of the other ones, for example, this M5 Stack Tough, this development kit includes a waterproof housing. It's not submersible, but the waterproof housing has a touch screen. It has all of the different bits that you would expect for these to have, and there is sort of a mil-spec connector on the outside. The case is UV resistant, and you can basically wire up whatever you need to. Well, again, the benefits of some of the other ones are the fact that we can stack other modules. The tough version, obviously you don't have that, but you can still wire up an external GPS sensor if that's the only thing you need. So I think that these are really cool because the price is great and the functionality is great. There are other things that you can get, such as the Raspberry Pis. There are very popular Raspberry Pis, and again, they come with Wi-Fi and Bluetooth. You can plug keyboards and monitors directly into them. There's an HDMI output on them. They're really powerful because the processor is great and they can actually be run as their own system. Again, you can run its own sort of Windows clone on it. You can do some basic internet searching, you can create documents, you can use it as its own development environment. So those are pretty cool, but again, you have the functionality where you need to add a monitor to it, and then you need to add a GPS module. And that's where I think the M5Stack stuff is really handy because, again, you can just buy the extended module. So in this case, you can buy the GPS module that you just stack onto the bottom of the case, and it really helps with the development. So there really is no predefined recipe for what you need. You can make a lot of these different parts work. Again, I've made the Arduino Unos work. I've made the M5Stack work. I have done some stuff, not in GPS module, but I've done some stuff with the Raspberry Pi. And you can really make any of these work, assuming that you have the correct parts. Now, the correct parts really come down to a basic microcontroller. Again, it can be an Uno, it can be any of the other ones. So again, I've used things like a Trinket MO or Qt Py, but these require you to do a lot more electronics building. You need to wire these things up, whereas the M5Stack is sort of a one-stop shop. You just grab it, you set it up and go. Throughout this series, we are not going to be walking through setting up the Arduino IDE. We're not going to be walking through setting up your specific board because they are so different. What we're going to focus on is going to be the basics of the program structure, understanding things like including libraries, what it means to have your setup and your loop. We're going to talk about basic graphics. We're going to talk about custom functions, how to draw a gauge, how to get information directly from the GPS sensor, how to display it on the screen, and some of the things that you might run into. So problems with things like data overrun or dropping signals or things like that. So we're going to talk a bit about some of those things, talk about where the project is going to go, and maybe some next steps that you can do. So if this seems like an interesting project to you, stick around. I'm going to be releasing a handful of videos on going through this. But the first step in the process, if you want to build your own, is to think about what parts you want to get and what you want to use. If you decide to go with an M5Stack and you decide to not go with the GPS module, there are some things that you should be aware of. So if you use the mini GPS unit like I'm using, the Groove connector is not going to plug directly in to all of the M5 stacks. And the reason I say that is because what M5 has done is they've color-coded these, which is really handy. They've color-coded them based on the communication protocol. Now, you don't necessarily have to know what that is, but just note that the ports are listed as A, B, or C. Now, port C is a UART. Now, it's a universal asynchronous form of communicating between the microcontroller and in this case, the GPS module. When we look at some of these development units, like the one that I have, the Groove connector is actually red, which means that it's the connector is an A connector, which means that it's I²C. So when you look down through the documentation, it can be kind of tricky because a lot of times the documentation will say Groove type C and they'll list I²C, IO, and UART, but they are color-coded. So red is going to be I²C or I2C, and the blue is UART, which means that they're not going to plug directly into each other. So for my project, at least for prototyping, I've had to take some jumper wires and jump the lines from the sensor itself directly to some inputs and outputs on the board, specifically pins 16 and 17, which is exactly where this GPS module attaches to. So when you're looking for parts for your project, there are some things that you should be aware of. You can see here that pin 16 and 17 is generally where it's going to connect on these units. That's where you want it for the UART form of communication. If you're doing this on an Arduino Uno, then you're probably going to have some sort of expansion board that plugs into the top of it that should already connect to the correct pins. But these are definitely things that you need to be aware of. Now, if you have trouble with that stuff, I will do my best to try to help out in the comments or through email. But again, there are a little bits and pieces, which is why I strongly suggest getting equipment and getting gear that is already designed to work together. Otherwise, there's going to be a lot of this sort of fiddling to try to get it to work. If you're using an M5Stack, again, the pins 16 and 17 are going to be for the UART protocol. This expansion option here where it plugs into the bottom should already work just fine for most of the units. You will note that they do list an exception here for the M5Stack Fire. Now, this is one of the units that's specifically for the Amazon Web Service, and that requires you to cut some jumper pins and solder some jumper wires to go to the correct UART pins on that unit. Most of the other units, the grays and the different newer units, these are all going to be able to use just pins 16 and 17, which you can easily access. So depending on the unit that you pick, you might have to think about those different types of things. Again, once you have it hooked up, it's pretty straightforward, but on this one, all of the pins are exposed on the side as well as the bottom if you remove the back, so it's very easy to just jumper pin 16 and 17 as well as 5 volts and ground to the sensor. And that is also true with Arduinos, whether it's a Mega or an Uno, and some of the other sensors, and again, Raspberry Pi. But keep in mind that we are specifically going to be using the Arduino programming language, the Arduino IDE. We are not going to be using UI Flow. We're not going to be using Python in this project. So just keep that in mind as well. If you happen to want to use a Raspberry Pi, I'm not going to be going through Python. However, a lot of the commands and the structure is going to be very similar, but the actual code that we use is going to be a little different. So think about the project. If building a GPS speedometer is something that seems fun to you, make sure that you do figure out what gear and equipment you want. Again, leave a comment on the video. You can send me an email, support@caducator.com, and I'll do my best to point you in the right direction. There will be some links in the description of this video. I'll put links to M5Stack, as well as the Arduino site, and also to Adafruit and SparkFun. Now, I'm not an affiliate of any of those. I don't get anything if you buy any of this equipment, so make sure that the choice is right for your projects. I've been really happy with the M5 stuff. I think that the build quality is great. The functionality is great. The support is all right. It does run, again, the Arduino IDE just fine. It can also run Python or UI Flow, so you can sort of pick and choose what you want to do. But I do think that those are really great units. But again, I'm not an affiliate. I don't get anything if you buy them. Just consider that it's a really nice unit, and it really helps save time with having to like solder or plug things in together, because you can just buy the correct modules, stack them, and it works. In this second part of our video series on creating a GPS-based speedometer, we're going to begin to cover the basics of the Arduino IDE programming language and what we need to know in order to complete this program. So the first thing that we should think about is, one, what board are you using? Now, if you opted to go with an M5Stack like I have, then it's important that you go through the M5 website and learn how to set up your board so that it can accept programs. If you're using an Arduino or some other variant, again, there is going to be detailed information about how to go through and set that up. This is one of the reasons why I really enjoy buying things from places like Adafruit and SparkFun, because they have such good documentation on not only their custom-made parts, but also the setup process. So I think it's important first that you understand how to set your board up. When you have your board set up, you should see it listed in the bottom right-hand corner of your screen. In my case, I have the M5Stack Core ESP32. It's important that we go through and we select the proper board that we're using. Again, in my case, it would be ESP32 Arduino, and then I would need to pick the M5Stack. You'll have to go through the list and figure out which board you're using for your program. Once you have that picked, you can also double check some of the other parameters, the upload speed, the flash frequency, the flash mode. These are all going to be determined. In some cases, these won't even be available, but they'll be determined by the board. And a lot of cases, you don't want to change these. So unless you have 100% certainty on what you're doing, leave them at the default settings. Next, you want to make sure that the port that you're communicating with your board is selected. In most cases, what you can do is you can select Get Board Info. If you have a lot of stuff plugged into your computer, sometimes you'll see a lot of different COM ports. In my cases, I'm on COM port 3, and that's where my M5 stack is connected. When we look at some of the other options, again, when you choose your board, when you choose your equipment, you need to make sure that you follow the recommendations to set that up. If you're using an M5, then there's going to be a different way to set it up if you're using Arduino as opposed to passing it some Python code, for example. So again, make sure that you go through that process and that you're all set up and ready to go. If you've never seen Arduino code before, if you're a 100% complete beginner, the first thing that I suggest you do is you take a look at some of the resources on the Arduino website, as well as go to File and Examples, and look at some of the built-in examples. Things like the basics. The bare minimum is what we get anytime we create a new sketch. A sketch is what Arduino calls our programs. But there's also things like digital read, fade, read analog voltage, and so on. When we look at some of these sample codes, such as Blink, this is usually the first one that people will go to. We looked at this when we did our video on Tinkercad circuits, so we have a little bit of knowledge on how to look at this and set it up in Tinkercad. If you haven't watched that, I think it's a great resource for a project like this because you can get in and begin to learn some of the basics, and a lot of these examples are already there. So in this case, what it's doing is it's going through the setup area, which is the area in which the code only runs once at the beginning of your program. So it's initializing the LED. It's telling the Arduino, whichever board it is, it's saying that this pin mode is our LED. The built-in LED in most cases is just going to be one on the board that's already pre-configured to a certain pin. You can also attach it to an external pin. In some cases, it'll be pin 6 or pin 13. And they're setting that pin as an output. And this is a critical step if you're using external sensors because you need to tell it whether that pin is expecting to read in a value or if you're expecting to output a value. For an LED, it would be a PWM or a pulse width modulation. That's going to determine things like how bright the LED is. Then the next section is the loop. And the loop is what happens over and over again constantly until you either disrupt the program with a reset button or pull power from it. In the case of our M5 stack, it's got a built-in battery, so we just have to double press the power button to shut it off. But what's happening inside of here is we're doing a digital write. And the digital write is setting the LED, the pin that the LED is attached to high or turning it on. It's waiting for 1,000, which in this case is 1 second. 500 would be half a second. 250, a quarter second, and so on. So it's waiting for that amount of time in the program, and then it's turning it low or turning it off. It's making the voltage go low. This is the basics of PWMing an LED, setting the pin mode to telling it that you're using an output on that pin, and then triggering it from high to low, basically pulsing it for, in this case, 255 would be full brightness or high, and then setting it low. So again, that's the basics of the simple Blink program. And anytime you start a new program, you have void setup and void loop. Now, these aren't the only loops or the only routines that we can run. These just happen to be the defaults. And generally what happens is you'll have things that have to happen before setup, and you'll have functions that you create after your void loop. What we're going to be doing is we're going to be talking about the M5 stack specifically in its LCD screen. But again, this is sort of a universal thing. When you're talking about any specific LCD that you're going to be using, if it's not an M5 stack, then you want to look at the documentation and figure out which libraries you need to include. Libraries are additional functions that are required in order to make most of these different components work. Whether it's a GPS unit, whether it's a stepper motor, whether it's some sort of additional math, then you want to include those additional libraries. For us, with the M5 stack, what we're going to be doing is saying pound include, and then inside of our arrow brackets, we're going to say M5 stack.h, and we're going to close that off and hit enter. Now, it's important that we note that some things will change color. So you can see that I accidentally was still holding down the shift key when I pressed the number 5 and I put the percent sign. As soon as I put the number 5 in, my .h is turned to orange, which means that it's able to find and reference that library. Now, if you're wondering what that .h file looks like, you can actually look for it on your computer. You just search for it wherever the library is stored. The libraries, if you had to download them, will typically be a zip file, but you can just search for M5Stack.h. And this will give you a list of different methods or functions that you can call and make different things happen. And again, the power of the M5 is that a lot of the stuff is already integrated. The LCD is already there, the speaker, the microphone, the SD card, they're already included. So as we look through here, inside of this LCD section, we have a bunch of different things we can do. We can draw a bitmap, which is pulling it from a file on the SD card. We can draw a JPEG. We can draw strings, which are texts, and we pick out the characters that we're using. We pick out the position and the font. Then we have things just like print. We can print variables or we can print strings. We can dictate the color, the size, and the position of the text by doing set cursor, set text color, set text size, and so on. We can also do things like create filled round rectangles, fill triangles, draw the outside of a triangle, circles. We can fill the screen with a specific color. We can draw a line, we can draw a pixel, change the brightness of the LCD. And again, because it's all integrated, we've got M5 button A, B, and C. We can tell if it's pressed or released. We can do a pressed 4, released 4 with millisecond value. We can also send codes directly to the speaker. If we want the speaker to beep, we simply just say m5.speaker.beep. So again, all of that is directly inside of that .h file. If you dig in deeper, the .h file is including a lot of other libraries automatically. And you can see that it's got sd.h, which is our SD card. We've got SPI, which is a form of serial communication. We've got wire, we've got Arduino.h. We've got the M5 display, utility config for button, speaker, power, and communications. And as you go through here, then it just gets into the code of what's going on. And essentially what's happening is the M5 code is calling all of these other libraries for us. So we don't have to put all of this different code at the very top. We're just calling the M5Stack library, which is then calling all of these other things. But the important thing to note here is that we have access to all of the different codes that we can run in order to make things happen. So now that we have the #include M5 stack at the very top, we can also start to define different variables that we want to happen globally in the program. So for example, if we want to define a constant integer for the minimum and maximum speed that we're going to have, we can say const, which is constant, int, which is an integer, it's a type of variable, and I'm going to set this at min speed is equal to 0. Now, whenever we're typing code into the Arduino IDE, we need to be very mindful of capitalization, but also of the formatting. Now, unlike Python, where it's really strict about things like the tab indents for understanding where things are inside of an if statement, for example, Arduino doesn't really care. The tabbing in is really more for visual formatting for us, but it does really care about things like capitalization, as well as putting semicolons at the end of lines. So for example, if I do const int max speed, and I say that is equal to 100, and I don't put that semicolon at the end, if I try to verify this, well, first I have to save it. So let's go ahead and save this program somewhere. I'm going to call this lead intro play, and I'm going to find a place to save it. So now that I have a place to save it, lead intro play, I'm going to go ahead and save it. Now I'm going to try to verify this code. It's going to compile. You see it's compiling down here. It's thinking, it's going through, and it should give me an error. It should tell me that I forgot something, essentially that it's expecting to have that semicolon at the end. Now, depending on the board you're using, the libraries you're referencing, and the code you're trying to compile, this may take more or less time. This is an unusually long amount of time for this to be compiling, but that's good because then we can talk about what's going on in the backend. Now, keep in mind that none of the setup and loop actually has anything happening. And you can see that the error that it gave me is highlighting void setup. But when we look at the error, it's saying that it expected something, either a comma or a semicolon, before void. So if we look back up the code, we come back up to the previous thing, we can see, oh, well, there's something that's missing there. So I'm going to go ahead and verify this again. It's going to run through, and this time it shouldn't find any problems. Now, verification happens when we go to upload our code to our board as well, but sometimes it's nice to be able to just verify it on the fly to make sure that everything's working. It's important also to note that when we're defining values, we need to be very specific and mindful about how we're defining them. Things like byte, int, float, these all take different amounts of memory. And this is where we run into problems when we're doing things like using an Arduino Uno, which may have limited amounts of memory, where if we're using an M5Stack, or maybe we're using one of the SAMD boards like the Trinket MO, they have a lot more onboard memory and sometimes expanded memory where you can solder on additional chips to get more SPI RAM. So in this case, it's done compiling, everything's fine. But we've defined two const integers. Now the const part of this means that it's not going to be able to be changed anywhere in the code. So what that means is I could say int current speed equals 50, and somewhere in my code I could say current speed equals 51, and that would be fine. But if I tried to say min speed equals 10 and redefine minimum speed, it would not let me because I told it this is a constant. It's not to be changed anywhere in the program. So if we're predefining some of these values, we need to think about where they're going to be used in the program. If these values are going to be used globally, things like the radius of a gauge we're designing or the XY position of the gauge, then those are things that we don't necessarily need to change unless you want to give the user the ability to change things like the size of the gauge, the position of the gauge, and so on. Things like the minimum and maximum speed, those are going to be constants. We're going to define the speed for our speedometer over a certain range of values. So constant integer for variables or values that we don't want to change anywhere, or just defining them as such as an integer for variables that we might want to conditionally change somewhere else. So let's go ahead and get rid of the current speed, and let's get rid of everything in void setup. Some other things that we can do is we can define additional variables at the very top by using pound define. In this case, what I'm going to do is define degrees to radians, as 0.017453292.5. That's a lot of variables there. The reason that we're doing that is because we are plotting something that is rotating in a circular fashion on a grid of pixels. And so we need to think about it rotating or sweeping through an arc of degrees, but we have to actually plot that out as if it is a radian value. We need to give it an XY coordinate. We can't just say this line at 5 degrees like we would in CAD. We have to actually tell it this is the position for the start of your line and this is the position for the end of your line. Notice that when we did this pound define, that we didn't say degree to radian equals 0.017 blah 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 and all that. Now the reason that we did it this way partially is because of the number of decimal places and potentially how we're going to use it. It's not really important that you understand the differences for these right now, but just note that there are different ways that you can define these various parameters that we're going to consider global. And you can do that at the start of your code. And the reason that I'm saying this is because if you download sample codes, you might see things pop up differently at the beginning And this might help understand a little bit about why. I know at this point we haven't really done very much of anything, but I've found through my sort of playing around with these that the hardest thing is to understand what's going on in these programs. And the way that I approach a project like this or a program like this is to figure out all the different pieces that I need to solve and solve them one at a time in programs. Now, if you have a lot of experience, you have done a lot of LCD programs or GPS programs and just programs in general, you might just instantly know what you need to happen. But as you're learning the process of creating these programs for these microcontrollers, then breaking it down into individual steps is going to be important. So I'm going to start by creating some comments and sort of filling out what we need to do. And then we're going to jump into CAD, and we're also going to jump into Microsoft Paint. So the first thing that I want to mention is that comments in the code will be skipped. The program doesn't care about comments. So anytime you see a single line with 2 slashes in front of it, that is going to be commented out. It's a place where you can just leave a note to yourself. We can also make a block of comments by doing the slash and the asterisk, and then anything that's inside of there will be commented out. So the slash and the asterisk is a great way for us to put a big block of code in that we only want to be reviewed as a comment. So I don't actually need the asterisk in the middle. It's just anything in between here is going to be a comment. So the reason that I want to do this is because there are a handful of things that we need to solve in order to make this work. Now, you can pick whatever order of operations you want to solve your projects. Generally, the way that I would approach something like this is first, I need to figure out what I want my gauge to look like. So first step would be figuring out graphics. Now, this could be, figuring out what it looks like and how it behaves. Now, how it behaves is interesting because what we need to think about is, do we just want to display a number on the screen, which is the super easy way to do it? Do we want to have some sort of needle sweeping through? Do we want to have, something a little bit more elaborate? So underneath here, we've got easy is going to be display a number. Harder, display a bar. And the hardest is going to be to display a filling arc. So that is sort of the first challenge to solve, is to understand graphically how that works. Now, unpacking that a little bit, underneath all of that, basics that we're going to need. These are things like for loops and if statements. We need to understand how to control the flow of the program. We're also going to need to know how to create our own functions. So these are custom functions, and we're going to call those every time we need to do a repetitive task. We also need to understand graphically the way that the screen display works. So we need to understand just graphics in general. Now, the way that we're doing this is going to be, I don't want to say the easiest way, but it's the most entry-level way. The reason I say that is because there are things like transparent sprites that we could use on the screen, we could move around, or we could display a JPEG or a bitmap image as the background or overlay of a gauge. And those are all things that we could do, but they take extra sort of steps to learn. And right now, understanding for loops and if statements and creating functions are the very basis of pretty much any Arduino program. The basics of graphics are going to be important, and understanding how to actually plot and display things. So graphics and text. And I think it's important to note that the LCD screen that is on the M5Stack is 320 by 240. I did mention before things like the micro view, which have the Arduino chipset already built into them. Those are much smaller. I think it was 32 by 32 pixels or 32 by 28. It's tiny. And depending on what screen you have for your project, you need to account for those variables and values when you're thinking about plotting, thinking about things like the radius of a gauge, the sweep of it, and so on. So those are some of the basics that we need to get out of the way for graphics in general. Now, some of the next things we need to understand are GPS. We need to know how to pull GPS data. So first, we're going to need to understand software serial connections. We're going to need to know how to initialize the GPS. We need to know how to read data and display it. Now, I think it's important from a GPS perspective that we do also understand that what we're doing is we're using a GPS module that will read a GPS signal 10 times a second. It's grabbing data 10 times a second, and we're grabbing it as fast as we can, and we're spitting it to the display. Anytime we put things like a delay in the program, we're messing with that data. Because we're not actually saving it or storing it in an SD card as a text file, then we're not really concerned with some other things that happen with this type of communication. If you're trying to do something like create a lap timer or a data logger, then you really need to be worried about data overflow or overrun, which is where the time that you're sending that data to the SD card, you're pulling in more data and you're missing bits of information. So that is a whole different level of trying to work with GPS data or work with serial data in general. That is outside of what we're going to be learning here. We're just going to grab a GPS speed and we're going to display it. And it doesn't matter if we miss 15 signals coming from the satellites, because we're only really concerned with what's happening at that exact moment. So, for example, if we put in a 1 second delay and we're only grabbing the GPS speed every second instead of 10 times a second, it doesn't really matter, because unless you're trying to get like a 0 to 60 mile per hour time in the like 3 to 5 second range, then you don't really care that the speed updates that much. So you have to sort of level set your expectations with what you're trying to get out of it. So we need to understand graphics, we need to understand GPS, and then if you want to go to sort of like the next level, you need to understand the buttons. Now, the buttons is sort of a general thing, and it's actually a very easy topic, but it's also complicated in the sense of this project. And there are a couple reasons why. So we need to know if the buttons are pressed and what to do. So in general, what we would do is we would have sort of a listener. We would be inside of our main loop, and we'd be thinking about checking if the buttons were pressed and then deciding what to do from there. Now, at a very general sense, we could do that and say, well, if you press this button, then run through this loop. But what happens if you press a button while you're inside of that loop, while something is happening? And the way that you handle that is with something called interrupts. Now, we are not going to be getting into interrupts and dealing with that in a sense of our program, but it is sort of like the next step. And the reason why you might want to do that is if you want to do things like change the color of the gauge or change the orientation of the gauge. If you want to go from a needle to a sweeping arc to just displaying a number. If you want to increase or decrease the brightness. Now, depending on the way that your function is set up, then those can be easier or harder problems to solve. But that's sort of like the next step. And the very last thing, and it really should come before buttons, but the very last thing is just kind of understanding what is happening. And the reason why this one is important, or a thing that we need to solve, is at the very top, we're understanding things like loops and if statements and custom functions. But when we're testing them out in a program, what we're doing is we're feeding it ideal data. We're saying, okay, well, here's some values from 0 to 100 miles per hour. Go ahead and plot them. But in the program, it's doing those things one at a time. It's saying, here's 1 mile an hour, here's 2 miles an hour, here's 3 miles an hour. Go ahead and start plotting those. In reality, what ends up happening is if you're accelerating, you might be at 4 miles an hour, then you might be at 8 miles an hour, then you might be at 15. And if you let off the gas, then you might be at 12. it's not going to go in linear order from 1, 2, 3, 4, 5 up to 12 and then back down. What it's doing is it's jumping around a bit. So if we develop a program that is expecting those numbers to happen individually, and we start feeding it these essentially randomized numbers, then it's not going to behave the same as it does in sort of an ideal or desk testing state. So we need to understand what is happening with the flow of data. So we're going to talk about all of these things. We will talk about the buttons in the context of the M5Stack. We'll talk about, obviously, GPS, the graphical stuff, and understanding what happens. Again, we're not going to get into dealing with data overflow or missing GPS signal. We're not going to get into configuring the different gauges with buttons and interrupts. But those are like next steps that could happen with these programs. But we want to get the basics out of the way. And at this point, I know we've already been sort of going and doing nothing for about 30 minutes, but we will get there, I promise. So let's go ahead and let's talk about the first bullet point, right? The basics of graphics. Now, in my case, what we're doing is a 320 by 240 pixel screen. And the way that I'm going to visualize this is in Paintbrush. So the first thing that I'm going to do is I'm going to resize this. I'm going to go to Properties. I'm going to set this at 320 by 240 pixels. So what we see on the screen, even though it says it's zoomed in reality, what we see on the screen, this is going to be our LCD. And the reason that this is important is that it helps us visualize what's going on. So in order to do this, I'm going to zoom in, but it is still essentially a 2-inch display. I'm going to go to the pencil tool and I'm just going to start plotting some points. So up here at the very left corner, this is pixel 1, 1. So in the X direction, we've gone over 1, and in the Y direction, we've gone down 1. Now, if I look at the bottom left-hand corner of Paintbrush, it will give you the pixel location of the pen. So what I want to do is I want to find 160 by 120. Once I find that, I'm going to put a spot there. So this right here, it's actually 4 pixels that have been colored in, but that right there is the center because it's half of our width and half of our height. Now, if we were going to program that in, what we would tell the Arduino in this case is we would tell it that the location of that is 160, 120. And we would tell it that we want the pixel to be black. The reason that this is a hard concept and that we really need to understand it right now is because those values are all positive. Because we're going over in the X direction, which is positive and that makes sense, but the Y direction, we're moving down, but those numbers are still positive. And what this means is when we begin to start plotting for a gauge, what we're going to need to think about is if we want the gauge to sweep, let's go ahead and draw a circle. If we want the gauge to sweep from the bottom center up around and go clockwise, what we're doing is we're drawing, I'll change the color here, we are drawing from this 160, 120 point, and the X is still going to be 160, but Y is now going to be 220, and that's positive. And then if we happen to come over, say over here, well, now we're at 60 by 170. So the center point is staying the same, but as we rotate around, these X and Y values are changing. And because we can't base our coordinate system as 0 from here, then we have to really think about these quadrants and these coordinates and how that works. And when we think about the angles, the way that we're going to do our code is this is going to be sort of our ending point over here, and we're going to sweep around from bottom center all the way over to the right. Now we're essentially sweeping 270 degrees, but this right here in the far right corner is 0, and it's expecting this position to be 90 degrees. And what we have in reality is we're going from basically minus 270 to 0. We're traveling around backwards. So that's an interesting and hard concept that we need to really think about before we really start to get into plotting. And there's another aspect of this that is going to be tricky for us to figure out, is we're going to take the degree that we're sweeping, we're going to feed it 0 to 270 degrees, and then we're going to convert that by using our degrees to radians. But we're also going to be using that to find out where the points are, because we're going to take the degree and radian value, and then we're going to take our inside and our outside radius values to get an X and a Y coordinate point for the start and the end of those lines. The reason that this becomes more complicated is because we can't just draw lines over and over again, because what ends up happening is as we draw those lines, we're going to get these little gaps between them. And instead of getting those gaps, the way that we're going to go about this is we're actually going to draw a bunch of triangles. So we're going to find our first point, and let's go ahead and do this with a different color. We're going to find our first point and our last point. We're going to sweep a certain amount of degrees. In this case, we're going to say 6 degrees, and we're going to find the start and end point of those as well. Now, the reason that that's important is because we're going to draw this. I'm going to use a different color still. Let's grab green. What we're going to do is we're going to say, let's draw a triangle going from here to here, and let's draw a triangle going from here to here. And then we'll be able to fill in those triangles. So by using fill, we can fill in those two triangles, and that's going to give us the position that we're at on our gauge. And that's why I said that just displaying the text number of the speed is the easy way, because once you start to get into these sort of arc sweeping graphics, not only do we have to think about polar coordinates or going from degrees to radians, we also need to think about things like how we're actually going to fill in that area. We could just sweep a line and that would be perfectly fine. But if you want to get that graphical representation of that bar going around, well, that's where this really comes into play. So let's take a quick look at a sample so we can see the 3 different styles. We can understand the different ways in which they're both easy and hard. So one of the styles is just to do a triangle. Now, this one's really easy because what we can do as we go along is we can say, we know that this bottom edge right here is always going to be at a certain height in the Y direction, and X is going to increase. So as we go along, let's say the speed is 30, let's say the speed is 50, let's say the speed is 70. That is going to be very easy to map along the X direction. What's tricky is that the Y direction is not going to be proportional to that. We have to decide if we want to just say the Y height is 1/10 of the X height or the X distance. And then we also have to subtract it, because remember, the further down the screen, the more positive that number is. So this is the easier way for us to do this graphically. And then, harder is for us to do these sort of filled in little sections, these filled in arcs, by doing filled triangles and then doing them every 6 degrees or so. So I know that was quite a lot. It is very important that you get your mind sort of framed around pixels, and you understand that when we're representing gauges or whatever you're representing graphically with pixels, that the orientation or the 0 position is generally in the top left of your screen, and you're moving over X, and then Y is positive, but it's going down the screen, which means that you have to sort of reverse your way of thinking about that. And then translating it to these sort of polar coordinates, going from our degrees to radians, that's another sort of step that is problematic, because you have to think about it not only in terms of positive and negative, but also converting your degrees, your sweep through the arc, to actual coordinates, and then translating that to things like an inside and outside radius. So now that we've got that sort of basics down, then I think it's important that we start to actually make something and display it on the screen. And this is where having your own code, your own M5Stack or your own display is going to be important. At this stage, we don't even need GPS at all. So if you have an Arduino with some sort of screen, whether it's a micro view or whether it's some sort of, 2, 3, 4, 5-inch screen that you can just slap on or connect to your Arduino. Make sure that you understand which libraries you need to include. If you're using one of the Adafruit products, it's generally like the GFX library, gfx.h, but go through the documentation and figure out which one you need. For us, what we're going to do is we're going to run through and we're going to just create some basic shapes. So we're going to learn how to do those basic shapes, and then we can understand from there how we can go through and we can start to plot a gauge. So on the right-hand side, I've got the M5Stack library pulled up so we can see that we've got m5.lcd. All these different commands. If you are using a different library, then your commands will be different. So the m5.lcd is only going to work if you are using the M5Stack. If you're using another library, then you'll need to make sure that you use whatever it's calling for. So if it's a specific GFX library, it might be something like gfx.lcd.fillScreen, or it might just be lcd.fillScreen or something else. But you need to make sure that you understand what those are. Again, with the M5Stack, we have it very easy because it's all already connected and it's all here for us. But the .h file of whatever library you're using will look the same as well. So we have some things that we define at the very top, our min and max speed and the degrees to radians. Those are all fine. I'm just going to leave those for now. But what we want to do is inside of our setup, we need to get things going. I'm going to use tab. I'm going to tab in. And with the M5, the first thing that we need to do is m5.begin. And that sort of initializes the M5Stack. We also are going to do m5.power.begin. And the reason we're doing that is because this gives us the ability to run it off the battery. So if it's connected to a USB and we're using external power, that's fine. But if we are running it off the battery, then we do need to make sure that we use that. Keeping in mind that there are different M5 units that have different available options, some that will deal with power a little bit differently. But in the most common sense, m5.power.begin should get things going and allow it to run on the battery. The next thing that I'm going to do is I'm going to say m5.lcd.fillScreen. And keep in mind that when we're doing this, it is very much case sensitive. The L in the LCD needs to be capital, F in fill screen, and S in fill screen, lowercase and capital respectively. And with the M5Stack and with most libraries in general, there are colors that are already predefined. So things like black is predefined, blue, white, red, green. In some cases, things like gray will be GRAY instead of GREY, depending on who developed the library. White is also there. Notice that these are in all caps. So when we're doing this, think about the way in which you want to sort of fill up your screen. In this case, I'm going to start just filling it with white. And universally, inside of the setup, I can do things like set my text size. So if I want all the text to be the same font size, I can set that here. If I don't set the text size or position, it's going to default to starting in the upper left-hand corner, and it's going to be size 1, which is really tiny, and for me, it's hard to read. So I'm going to do m5.lcd.set text size, and I'm going to set that at 4. So at this stage in setup, all we've done is we've started the M5. We have said, go ahead and use the battery, go ahead and use power, and we've also filled the screen with white. So by doing this, if we just run this code, which again, the setup only runs once, it should turn the screen on and just have it display white. To make sure that it's working, I'm also going to just put some text on the screen. Now with the text, we can either just print the text or we can tell it exactly where we want it to be. So I'm going to do m5.lcd.setCursor, and then I need to give it an XY location. And for this, I'm just going to say, go over 10 pixels in the X direction and go down 120 in the Y direction. That's going to be about halfway. And then I'm going to print something on the screen. So M5.LCD.print. So with print, there's actually 3 different types of print that we have. We've got printf, and we have println. And they behave a little bit differently. So for example, if we do println, then it will have a text wrap on it, and printf generally won't. It'll just keep printing from the last text that you put on. So if I do println, I'm going to put double quotes in here, and I'm going to just say M5 space test, end it with double quotes and the brackets, and put a semicolon. I'm going to say delay, D-E-L-A-Y, and I'm going to delay 100 or 1/10 of a second. I'm going to then do M5.LCD, and I'm going to do println again, and I'm going to do graphics, and the double quotes and the bracket, semicolon, and I'm going to do a delay for a second, and then we're going to clear the screen. So we're going to do M5.LCD.print, actually M5.LCD.fill screen, and we're going to go ahead and just fill it with white again. Now, keep in mind, if you fill the screen and you just continue to do things like text with the word wrap, or if you just print, it will still know that the text was there, but all you're doing is you're overwriting the sort of the image on the screen. You haven't really reset that unless you're specifically telling it where you want the text to go. It's still sort of kept in the buffer. So at this stage, I'm going to save this, and I'm going to upload it to my M5Stack so we can see what's going on. So you can see as it's uploading, it went through the process to verify it or debug it, and now it's uploaded. So if we take a look at this on the screen, we can press the reset button to run back through. And by default, so if we're looking at this, by default, the text is white because we never told it what the text color is. So if we want to see this a bit easier, I'm going to go ahead and change the background to black. And we'll go ahead and make this one black as well. We could also use the text color. So you can see here that we can set the text color. And there's also a background text color because the font, each letter is going to take up a certain amount of space. So we could set the font at black with a white background. In this case, I'm just going to reset the black background. I'm going to go ahead and save that and upload that so we can test it as well. So we can see there that now the background's black, the text is white. It's 10 pixels in from the left, and it's about halfway down. So at the very basic level, what we've done is we've defined the M5 to start running and to be able to run off the battery. Now, if we're running off the battery, all we have to do is double click the power button and it'll cycle the battery off. And then it's filling the screen black. We're setting the text size at 4. We're telling it exactly where we want the cursor. And then we're starting to type. And println, when it starts to print, it's going to go down to the next available line. It knows the font size because we set it at 4. And it's just going to move it down so that the font is below that. So using println is pretty handy. If we change this to just print or printf, then it's not going to go down to the next line. So little things like this using println can make your code a little bit more readable. This is, again, very basic. We can do some slight changes, but I'm just going to leave it at that for now. This only runs once inside of the setup and never again. So it's only the very beginning. Now that we have a basic understanding on just the initialization of the M5, filling the screen with a certain color, setting the text size, setting the cursor, and just sending some text to the screen, let's look at how we can actually go through and draw some different shapes. So drawing shapes takes the sort of the same basic idea, and we just have to feed it whatever line of code we want. So for example, if we want to do a fill circle, well, if we do a fill circle, then what we're going to do is we're going to feed it x and y. So it says int 16 underscore t. It's just a different way to define an integer as 16 point precision. You can see that we got x and y. We're going to give it a radius value, and we're going to tell it the color. So in our setup, the last thing that we did was we set the screen to fill with black, which means at this point in time, the screen is black. So what we're going to do in our loop is we're going to start by using a fill circle. This is going to be the easiest thing for us to do. We're going to go m5.lcd.fill circle, and we're going to give it an x and y value. So we're going to say 160, which is in the middle of the x direction, 120, it's the middle of y. Radius, so keeping in mind that 120 is in the middle vertically, so that is going to be 240. We want to make sure that we're not bigger than that. So I'm going to set the radius value at 100, which should give me a 200 pixel diameter circle. And then I'm going to set the color. I'm going to say red, and I'm going to finish this off. Now, in this program, it's going to continuously draw that red circle. So it's going to go over and over again. Now, we have to think about, does that even make sense? So at this point in time, it's not going to be clearing the screen, so we're not going to really get any flickering, but let's go ahead and let's just upload it and see what this looks like. So we can see now that we've got a red circle drawn directly in the center. We have to sort of think about drawing graphics on the screen as happening in layers or in order. So if we drew a smaller white circle or a blue circle, whatever color, if we drew a smaller circle after the red circle, then it would display on top of it. However, if we drew it before the red circle, then essentially what we would be doing is clearing it out. So I'm going to do m5.lcd.fill circle, and I'm going to go ahead and put it at the same location, 160, 120. This time I'm going to say the radius is 80. And I'm going to say white, and I'm going to go ahead and take a look at what that looks like. So there's some interesting things happening here. Now, the reason that some interesting things are happening here is because it's constantly redrawing the red and the white circle, and it's happening at the same time. So what's going on is we're never clearing it. The red and the white circle are always there on top of the black background that happened in setup. But it's drawing the red circle and then the white and then the red and the white and over again. So what this means is that we're getting sort of a flickering, and we're only getting a flickering where the white circle is happening over the red circle. And there are a couple ways that we can handle this. First, we need to think about, do we actually want to redraw the screen? Now, in the case of updating speed, well, yes, we want to redraw it every time we get a new speed, or in the case of our GPS Speedo, we're just going to constantly update it based on whatever speed is read. But in reality with graphics, we don't really want to constantly update them because we don't really want that flicker unless we have to have it. So one thing that we can do is we can slow down the program. So after we draw the red, we can put in a delay. And I'm going to go ahead and put in a delay of 500, which is half a second. And what this means is it's going to delay the red being drawn. It's going to draw the white. I'm going to delay it another half a second. And then what I'm going to do is say m5.lcd, and I'm going to fill the screen. And we're going to fill the screen with black. So we're going to do the same thing that we did in the original setup. And then I'm going to toss another delay in here. Now, delays are tricky because we're not actually working on real timing here. What we're saying or what we're doing is we're putting an artificial pause in the program. There's nothing to say how long it takes for it to fill the screen. There's nothing how long it takes for it to draw the circle. But what we are saying is that we want to delay the distance or the time between each of those things happening before the next thing happens. So if we were dealing with passing data back and forth, this can be a very dangerous thing because it leads to data loss. We drop data if we're not handing things off at the right time. So this is not an ideal case, But if we're just dealing with putting graphics on the screen and the time of it doesn't really matter, well, it's not really a bad thing. But what we're doing is we're slowing down the overall process. So let's go ahead and let's take a look at what happens with this code running. So now we can see that we've got a black screen, we draw the red circle, we draw the white circle, and then we wipe it all out. So we're no longer getting that sort of flickering look that we got when we were constantly just redrawing the red and white over and over again with no delay. Now, a 500 or half a second delay is a little bit excessive, but again, it just sort of proves the point that we only really should do things when we need to. So if we're talking about erasing part of a speedometer, if it's a needle or an arc, we don't want to constantly be doing that over and over again. We want to think about the timing of everything. So when you're passing speed from a GPS sensor to a gauge, you are collecting that data 10 times a second. If we are also passing that data 10 times a second directly to the LCD screen, that might be a bit too much, when in reality, we could just send it every half a second or every second. And even though we're dropping a little bit of data, we're not really worried too much about the speed getting up or going down as much as the current speed we're traveling. So a second might be a bit extreme, but hopefully that sort of drives the point of just sort of getting to your position, or, falling back down from a higher speed to a lower speed. We don't need to really update that 10 times a second when we can slow it down to every 1/10 of a second or quarter second. Maybe even faster than that. It just depends on what the graphics are going to look like. So now that we've got that basic bit out of the way, I'm going to go ahead and wipe all of that out, because that was just the initial test. Now that we understand how we can create a fill circle, we need to think about how we can actually create our gauge. Now, again, the easiest way for us to do a gauge is just to display text on the screen and pass a value to it. But that's not going to look very good. Now, sure, it could work and it could be very visible, but we want something a little bit more extravagant. We want a sweeping arc, because that's the hard thing to do. So now that we have these basics down, I want you to start thinking about the different triangles. When we were looking at this in Paintbrush at this extremely precise drawing, we need to think about these different points that we're going to be drawing, right? So we're going to be finding, I'm going to go ahead and change this to purple. We need to find this point here, this point here, this point, and we're going to pass 3 coordinates for this triangle, and then 2 of those coordinates are shared, so we just need to find a 4th coordinate to pass to that triangle. And the way that this is going to work is we're going to take the current speed, no matter what it is. So let's say the current speed is somewhere over here. What we're going to do is we're going to take that current speed and we're going to fill in everything below it. And then if the current speed goes up to a higher value or down to a lower value, we're going to wipe the entire gauge, and then we're going to redraw that current speed and everything below it. So that's the way that we're going to do this, because again, when we're testing these things out and we're just feeding it 1 to 100 in a very linear fashion, it's very easy for it to draw that sweep on the screen. However, when we start passing it real values, it might be 5 miles an hour, then it might be 15 or 20, then it might go to 30, then it might go back down to 20. Well, then it has trouble figuring out, like we can't just say, oh, we're going to always pass you the next higher up or the next lower down value. We need to just think about it from the most idealist and simplest standpoint of, this is your current speed, let's just fill everything below it, because it happens instantaneously. We're not feeding it tons of data, we're feeding it one value, well actually 2 values, current speed and last speed. And we're saying, all right, well, take this value and then just fill in this gauge. And it's going to happen faster than we really want to pass the values back and forth. So before the next video, think about that. Think about the coordinates that we're going to have to figure out. And if you have the ability, think about the math behind it. We're going to be using sine and cosine of the angle. So we're going to be Essentially what we're doing is we're passing a value from 0, saying this is 0 down here, to 100, and we're going to use a function called map, and we're going to map that value from 0 to 270. So it'll know, for example, if we're at this position right here, it will know that that's 180. Even though the speed is not 180, it's going to pass that 180 value. And then we can take that angle and some other parameters that we're going to give it, things like the outside radius of the circle, the inside radius of the circle, and we are going to pass those and that angle to get our coordinates. And then we're going to use some arbitrary numbers like 3 degrees or 6 degrees to increase or decrease that value to get the rest of our triangle. And this is horrible drawing here, but hopefully you get the point. So think about that. Think about how you would do the math aspect of it if you can figure that out. And in the next video, we'll tackle the math portion of it, and we'll get this to plot a gauge. We'll feed it some fake numbers just to display it on screen. We'll go from 0 to 100, but we'll take care of learning to map those values, the min and max of our gauge to the min and max of our sweep, 270 degrees. We will learn how to calculate those coordinates, so that way we can update the radius of our gauge, we can update the thickness of that section, and we can just take care of all of those global variables very easily at the start of our program. And then we'll also go through and we'll do some looping. We'll do a for loop of going from 0 to 100 and back down to 0, so we can just do a test to see what this gauge looks like. Before we go too much farther, let's hop back into our program here and just remember the things that we need to learn. So graphics, easy, display a number. Well, that's simple. We already know how to do that. It's just passing text. Instead of passing something like M5.test, what we would do is we would just pass it a variable like max speed or current speed, and that would display the number on screen for us. So that one we got. Harder is to display a bar, and that's going to be that sort of growing triangle. We already know how to do simple graphics. We can do a circle, we can do a triangle, we can do a rectangle. All of those are easy. We know the codes that we need to do it. When we do our test with our numbers, we'll do both the bar graph and we'll do the sweeping circle, just so that you can have a baseline for how both of those work. And then we're going to tackle the filling arc. That's sort of the hardest graphically. There's actually one level above that if we want it to sort of start out horizontally, ramp up, and then end horizontally, but I'm not even going to go into that one. I've played around with that using, trying to do some logarithmic functions, but it's just too much. So we're going to do the hardest one as filling that arc. Once we tackle all of that stuff, we'll have a good grasp on for loops and if statements, creating our own custom functions, and dealing with displaying graphics on the screen. From there, we'll move on to getting GPS data and then understanding how we're going to pass it all back and forth. Now we need to get to the for loops and if statements and creating custom functions. And at that stage, what we're going to be doing is we're going to be creating a sweep gauge that creates a triangle. We're also going to be creating one that's a needle, and then we're going to be creating one that's the arc sweep. So the thing that we need to think about is how we want to sort of parse out the different aspects of a program. So when you think about a program, you have to think about repetitive tasks, things that happen over and over again. And then you have to think about what kind of information those repetitive tasks need to be completed. Now, in most cases, what you're going to be doing is you're going to be creating custom functions to do little bits and pieces of your program. Right now, we have our void setup, which runs through, it displays the text, the black text, or the white text on a black background. It does M5 test and graphics. And then in the void loop section, we haven't done anything yet. So what we're going to be doing in void loop is we can either look for things like button presses, or we can call to separate functions, things that we want to happen over and over again continuously until we sort of pull the plug and take the power off of this device. So the way that we're going to do this is we are going to create our custom functions. And there are a couple things that we need to know about custom functions. I'm going to go outside of these brackets because everything inside of those brackets happens inside of void loop. And outside of these brackets, we're going to begin creating our new custom functions. Now there are a couple different ways that we can do this. So void is a keyword that's used when we're creating these functions that means that it's not going to return any values. So essentially, we're going to call to the function. We can pass it some values if we want to, but nothing is going to come back from it. So that's a key that we want to think about. If we just want something to happen inside of the function, we don't really care about any variables, then we can use that as our go-to. But there are other ways that we can define functions as well. If we're expecting to return a value back from our function, then we would want to define it with another term. Now, so we could have a function called void try sweep, and that's for triangle sweep, and then we would need to use our curly brackets. Anything that's inside of those brackets is going to happen inside of that program and that function. We could also create one using int. So if we were going to pass and expect integers to be returned, for example, this int term would be perfectly fine. We could simply say int, and instead of our try sweep, maybe we do a needle sweep. And again, curly brackets and so on. So those are the two main differences. And for our program, we are not going to expect anything back in return. Anything that we need to happen is going to happen inside of this program. So I'm going to be using void for all of mine, and I'm going to create 4 separate functions. So we got try sweep, or the triangle sweep that we're going to do. We've got needle sweep, and I'm going to do a void arc sweep. Now, for right now, as we look at these, the brackets are empty. Now, that's fine. We don't actually have to have anything in those brackets, but anything we put in those brackets are going to be variables that it expects to be passed. So for example, right now, if I want to call to try sweep, up inside of my void loop, all I would say is try sweep with the brackets and a semicolon. And that would instantly call to this program, this void function. It would run anything that's inside of here, which there's nothing yet, and then it would hop back in to the next line in my void loop. If I wanted to pass it something like custom speed, well, then what I would do is I would expect to pass a variable. So let's say that I wanted to pass it min speed, which is set to 0, and max speed, which is set to 100. If I were to pass those values in, I would need to declare them inside of my void function. So inside of here, I would need to declare not only the value, but the type as well. So int, I'm going to call this one start speed, because remember, the min speed and max speed are global variables. So theoretically, I don't have to do this because I could just use them anyways. But if we were going to pass them back and forth, then I would want to create something like this. So now, when we call to this function try sweep, we are sending variables from our loop, and we're sending them down into the function that we're running, try sweep. The reason that this is important is because when we finally get to grabbing our GPS speed, we're going to be grabbing it in the loop and then passing it directly into our functions, the ones that we want to use to display on a gauge. So this is the process, or this is the way that we would do it. Right now, we don't need to worry about passing anything, but I just thought it was important that we understand the differences of the way in which we can pass values into these. So what I'm going to do in my main program is I'm going to say try sweep. I'm going to do a delay in here of 1 second, and then I'm going to call needle sweep. I'm going to do another delay of 1 second, again 1000, and then I'm going to do my arc sweep. Remember that the capitalization is important, and we need to make sure that it matches whatever we have typed in. So from here, we need to think about a handful of things. Does everything that gets drawn on the LCD happen inside of this loop, or do we need additional functions? Like, do we need a function to generate the speed, or do we need a function to draw certain aspects of the gauge? Now, in reality, with the final program, we are going to want to have other functions to do things like draw or clear the gauge, or to display the speed, or all these different bits and pieces. But for right now, we don't really need to worry about sending anything back and forth. All we need to do is In the loop, we're going to call to each of those functions with a little bit of a delay between. And inside of each of these functions, we're going to be building out our loops in order to actually produce something. So we're going to start with the try sweep, and then we're going to see what it looks like. So inside of our try sweep, now is the point, because we don't actually have a GPS speed, we're not passing in a value, now is the point where we want to create a loop that goes from 0 to 100 or 99. So we're going to do this with a for loop. And the way that we structure a for loop is just by typing for, having some brackets here, and inside of those brackets is going to be our condition for the for loop. And then at the end, we'll have our curly brackets. So anything that happens inside of the curly brackets is within that for loop. So inside of the for loop, we're going to define an integer. The integer is going to be I, and we're going to set that equal to 0. Now, there are 3 conditions that are going to be inside of our for loop, and we need to separate them with semicolons. So the integer I equals 0 is our starting point. Now we need to tell it what the ending point. We're going to say I is less than 99. So it's going to go up to 99, or theoretically it's going to stop at 98. Semicolon, and then we're going to tell it how much to increment each time. So I'm going to say I plus plus. So it's going to go up 1 mile per hour, theoretically, each time it goes through this loop. Now that we have that information, again, the formatting is not really critical for the program inside of here, but it is important that we do have something just for ease of viewing this code. And I know this is kind of down here. I'm going to go ahead and just pull it in the middle of the screen. Maybe it might be a little bit easier to see. So now we have our beautiful drawing in the background, and we've got this void try sweep, and we've now got our for loop that iterates from I equals 0 to I equals 98, and it's going up 1 mile per hour each time. Now is the point where we need to map that, because we're giving it a speed from 0 to 100 theoretically, and we really want to have a degree value. The degree value is from 0 to 270 if we're talking about an arc. In our case, we actually want to map it for the entire width of our LCD. Mine is 340, so we're going to map it for that 340. Here is another thing that we could put in a variable at the very top. So I could say const int LCD width, and I could say that's equal to 340. Then I could do another const int LCD height, and that's equal to 200, I'm sorry, yeah, 260, no, 240, 320 by 240. So now that we have those constant ints defined, we can use them anywhere in our program. So we're going to map a new value, and I'm going to call this int width map. And this variable is just a name that I came up with. It can be anything you want, as long as it doesn't coincide with another term that works inside of the program. So you'll note if you just type in the word max, max actually means something, so you can't just use that term. But int with max, I'm saying this is an integer, and we're going to use a function called map. And what map allows us to do is it allows us to take I, so we're mapping this I value that we're iterating through from 0 to 99 or to 98, and then we're going to use a comma, and we're mapping it based on our minimum speed and our max speed. So I'm going to type min speed, max speed. Those are global variables, so I can pull them in at any time. And then we're going to go from, we have to think about this programmatically, because what we're doing is we're mapping the width from 0 to 100, and we want to map it from 0 to 320, whatever the width is of our LCD. So we're going to map that from 0 to our LCD width. So LCD width, which is going to be whatever we defined at the very top. Now, the reason that this is important is because it gives us very easy access to modifying our parameters. So if I want the gauge to go to 120, I can just modify it here at the top. If I want it to go to only half of the LCD, then making adjustments here at the very top is going to affect all the gauges, assuming we reuse those values. And that's why global variables are very nice. So we've got this mapped from I, the current I value in the for loop, from 0 to 100 is now mapping it from 0 to our LCD width. So close the brackets, semicolon, and now we have a variable width map that we can now use to define our triangle. The other thing that we need to do is we need to figure out what the height is going to be of our triangle, because as the speed gets higher, as the triangle gets wider, we want it to get taller and we want it to maintain some sort of relationship. So I'm going to call this nth height map, and I'm not actually going to use the map function, but just to keep it consistent, this is going to be equal to, we need to think about this again in terms of the coordinates on the screen. So if you want the actual height of your LCD to start at, let's say, 200 pixels down, then we would want to say 200 minus, and I'm going to put in brackets, our width map divided by some number. All right, so what we're doing is we're essentially saying whatever the current value of width map is, we're going to take that value, divide it by 8 to get the height of our triangle, but then we're going to subtract it from 200 because we're going to put the entire thing 200 pixels down. All right, hopefully you're still with me. And again, this was one of the easier ways for us to do the gauge, which I think it's important that we start here because otherwise we're just going to get lost in the math. So now we've got some values here. We've got our width, which is growing 1 mile per hour or 1 pixel at a time, and that's mapping to the entire width. So instead of just moving 1 pixel over, it's going to map this entire value to go 320 pixels wide once it gets to 98, or to theoretically to 100. So it's going to take I and it's going to map those for our min and max speed over to our min, 0, and max width of the LCD. Then we take the height and we create a factor of the width. And now we can actually draw something. So we're going to go back to our m5.lcd.fill screen. We're going to go ahead and fill the screen black. And then we want to do our fill triangle. So m5.lcd.fill triangle. And when we have a fill triangle, we need to pass it 3 sets of coordinates: x0, y0, x1, y1, and x2, y2, as well as a color. So it's going to go from 0 in the x direction always. We always want it to start at 0 or whatever number you want it to start at. Then we're going to go down 200, and we're only doing that because this is the pixel value that we said we were going to start at for our y. And then the next point is going to be whatever the current width is going to be. So width map is the current x, and then the y is still going to be 200. So basically what we're doing is we are drawing, let's go ahead and go over here. We are drawing this bottom line, and then we're figuring out what that third point is going to be. So the third point is going to be width map, and it's going to be our height map. And the last thing we need to do is give it a color, and I'm going to say blue. Now, if you're wondering where all of this came from, again, this is in the .h. So if we take a look at the fill triangle, which is this line right here, it's expecting x0, y0, x1, y1, x2, y2, and a color. So it wants x and y coordinates for 3 separate points. Now, if we think about what's happening here, we are taking I of 0. So I is 0, it's going to plot out 0, so nothing will happen. When I goes to 1, it's going to map 1 from 0 to 100 across the entire LCD. So it's going to go to, let's say, 30 pixels in the x direction, and then it's going to take that, divide it by 8, and minus it from 200 to give us the height that we need. Then we're going to plot the first point, which will always be 0 to 100, the second point, which will be based on the current plotted width map, and that's always at 200 as well. It's the bottom of our gauge. And then we're going to go to the third point, which is going to be the width, this upper point here. So again, as we go through, it's going to sort of redraw this. Now, the trick to this is each time it goes through this for loop, it's going to do the same thing over and over again. So it's important that we blank the screen out and redraw the entire triangle. While it isn't strictly required because we know we're creating this sort of linear transition triangle, if we were to come back and try to make the triangle smaller, say we were slowing down, then we are going to have a problem because essentially we're just drawing a smaller blue triangle over a bigger one. We're not going to be able to sort of tell what's going on. So we have to clear the screen first or put a black fill screen on before we can redraw that triangle. So before we go any further, let's just see if this works. So let's go ahead and save it. And then we're going to make sure that we upload this to the M5Stack and see what happens. Keep in mind that needle sweep and arc sweep don't do anything. But what we should see is that the try sweep does create this triangle map. We don't have any delays in here yet. So if you want to slow it down, we can go ahead and add a delay. But keep in mind it's going from 0 to 100. So we don't want a long delay. Otherwise, this is going to take quite a while. So I'm going to go ahead and upload that. And then we can go ahead and take a look and see what happens. So we can see here that we got an error, and it's simply because I don't have an equal sign in here for the map. So let's go ahead and resave that and try to upload it again. So as we can see, everything appears to be going right. The blue triangle is growing from left to right because we don't have anything else in needle sweep or arc sweep. Nothing else gets drawn, but it goes through, it draws that, it exits and goes to this delay, then it goes through each of these, which again, nothing happens. So essentially we just have a dark screen, and then it goes back into try sweep. So it keeps doing them over and over again. So if we wanted to actually get it to come back down, we would just have another for loop and we would repeat the same process. The main difference is with the new for loop, instead of going from 0 to 99, we're going to go from 99 to 0. So I'm going to take this entire for loop and I'm just going to copy it and I'm going to paste it here. If I box select everything, I can use Shift and Tab to bring it back to the left. I'm just going to say I equals 99. I'm going to say that it's greater than 0. And we want to subtract. I'm going to do I, and instead of going down 1 each time, I'm going to do minus equals 5. So I is going to go down 5 each time from 90 to 0. All the rest of it should be exactly the same because all we're doing essentially is we are clearing the entire screen and we're mapping it to wherever the current I value is. And that's kind of the benefit of using this triangle method because it's really straightforward for us because we can just clear it and keep drawing it. So let's go ahead, save, let's upload this and let's see what it looks like. So one thing that we can see is that when the triangle is getting smaller, it's happening a lot faster, and that's because instead of going up 1 mile per hour at a time, we're going down 5. You'll also note at the very end that it actually leaves a small amount. Part of that is because I didn't go from 99, I went from 90, and we're going down to 0, but we're not including 0, and we started at 0. So in order for this to go all the way down, I either need to set this at 1 at the very beginning, or I need to set this to greater than or equal to 0 by adding the equals. Either of those will be fine. I'm okay with just leaving that last little bit there, but those are just a couple things that you can think about when you're playing around with these. So now that we have the triangle sweep, we can start to think about potentially more advanced ways that we can do this. I'm just going to clean up the code a little bit, make sure that things are formatted nicely. My for loops are in the same sort of area, and I've got my brackets in line with the for. So again, it's just kind of easy for me to read, and this is in line with the try sweep. So the next thing that we want to do with the needle sweep is very similar. We're going to do a for loop that goes from 0 to 99 and from 99 back down to 0. However, this time, what we're going to do is we are going to sweep a line. So if we bring back our library.h, what we're going to be doing is drawing a line, which is this one here. It's expecting x, y for the initial point, and x and y for the second point, and then a color. Now, there's a couple things that we need to think about in terms of global variables. So I'm going to create some more ints up here, and I'm going to keep them as constant ints. And I'm going to call this one gauge rad for gauge radius. And I'm going to set this at 90. I'm going to call this one const int gauge width. And I'm going to set this at, let's go ahead and let's just set it at 50 pixels for right now. And so those two values right there are going to help us determine not only the diameter, or the radius of the arc of the gauge, but also how wide the needle is going to be in this case, and eventually the arc that we're creating. The other things we need to think about are going to be things like the center of the circle, essentially the circle, because that's what we're using for the sweep of the line. So when we think about that, we can use the values of LCD width and height and just sort of restructure those. So I could do const int LC, so this value is going to be my X LOC for X location, and this is going to be equal to LCD width, and I'm going to divide that by 2. So that's going to give me that location. Const int Y location is going to be LCD height divided by 2. This is also a great time to think about any other variables that we might need. So let's go ahead and add one. Const int, and these don't have to be defined as constants, but it does help prevent from changing them later on and lets you define them very early on in the process. So I'm going to call this width. Actually, let's call it gauge delay. And we'll set it just equal to 50 for right now. We can change that later on. So now we've got our radius and our width. We've got the LCD width and height values. Those are used for mapping, so we're using these for mapping values. And then we also have our X and Y location, which right now is half of the width and height of the LCD. We could also manually change those if we wanted to, let's say, create a couple different gauges. We could call the function and simply put it in 2 different locations. And then we've got just a random delay value. So this keeps us from having to manually put in delays if we want to sort of pause gathering information from the GPS sensor, or if we want to slow down the drawing process, then we can just use that gauge delay. So now that we have those values, and you could keep any other values, things like colors or any other parameter that you might want, now we can just use those inside of our loop. So what I'm going to do is I'm going to copy these 2 for loops and place them down here. And the reason that I'm doing that is because this allows me to just reuse this program that I know, and I don't have to fill the triangle because that's not what we're doing. I'm going to go ahead and get rid of the fill triangle. And then inside of the delay, I'm going to just type in gauge delay, and I'll do that up here. And that was that value that we used. And of course you can copy and paste this, but again, the reason that we would do this is so it gives us a single location to change these values. Instead of having to go in and find everywhere in the program that we used that value, we can just go back up to the top and say, well, I want to slow it down, so let's make it 150, or I want to speed it up, so let's make that 5. So it just kind of helps out programmatically to figure that stuff out. So now in the needle sweep, we have to think about the fact that we are no longer mapping the height. We actually don't need the height map at all. And what we're actually trying to do is we're trying to find the points based on a sweep of an arc. One of the differences now is the fact that we're not going from 0 to 100 and going up to the LCD width, but now we need to think about the number of degrees that we're going to sweep the arc. So we're going to do 270 because we're going to do 3/4 of the full circle, keeping in mind that the 0 position based on the actual coordinates is going to be the 3 o'clock position. So we're starting at the 6 o'clock position and sweeping around clockwise, which is going to be negative 270. So now that we are mapping those values, we're passing it 0 to 270 essentially. From 0 to 99, we're passing it 0 to 270 mapped. Now we can fill the screen and we can find our coordinates. Now the coordinates here are going to be based off of this I value and, well, really the mapped value. And instead of width map, I'm going to change this to arc map. So the reason I'm doing that is just to keep the terminology more in line with what we're doing. So let's make a little bit of space here and let's think about this. So what we're going to be doing is creating some new values, and I'm going to use float because we're going to have a lot of decimal places. And I'm going to create an SX variable, and that's going to be equal to some math operators. We're going to use cosine, and we're going to do double brackets, and it's going to be our arc map minus 270 degrees. We're going to close those brackets, and then we're going to multiply it by our degree to rad. And that degree to rad was that value that we had at the very beginning, that pound define. And this is essentially how we're going to convert 1 degree to radians. So down here in the needle sweep, what we've essentially done is we're figuring out the x and the y value, and then we're going to be using the radius value and the width of our gauge in order to find our x and y coordinates. So again, because of the number of decimal places, we're going to use float, and this is going to be sine, and it's going to be arc map minus 270, and again, we're going to multiply that by degree to radian. So at this point, we now have this x and this y value that we can translate out to our radius and our coordinates for where our gauge actually is. And in order to do this, we're going to define some new int terms. So at this point, we've just used int, which is kind of a placeholder, but there are other types of ints that we can define. So if we specifically know that we have a uint 8 or 16, then we can use those values. And the reason that we would want to do this is because we want to really think more about the memory management of the amount of space that we need to take up with these variables. So floats have a lot of decimal places. So when we're doing our ints, that is sort of a generic integer value that could technically take up way too much space. If you had, let's say, a byte, you could use the byte term. In this case, we're going to use uint 16 underscore t, and we're going to find an x0 coordinate, and that's going to be equal to sx, and that's going to be multiplied by our radius minus the width. So if we think about those variables we've got our gauge rad and gauge width. So this is our gauge rad minus our gauge width, and then we're going to add our x value. And our x value at the very top was our x LOC. So x capital LOC, and then we're going to finish that off. We're going to define this again, uint 16 underscore t for y0. We're going to do the exact same equation, but this time we're going to use sy, and we're going to multiply that times our gauge radius minus our gauge width, and we're going to add the y location. So this is the first point for our line. The second point for our line, we're going to define very much the same way. So I'm going to copy these and I'm going to paste them down here. The main difference now is we're not going to be subtracting the width value. So we're going to get rid of the width in both the x and y. This is going to be y1 and x1. And essentially what we've done is we found the point on the gauge where the width, or essentially the inside radius and the outside radius are. Now, if you wanted to define this as the gauge inside radius and gauge outside radius, you could have done that, but we used a width value. So let's unpack this just a little bit, because a lot has happened inside of this bit of code, but this is going to be the basis that we're going to expand on to do the arc version of this. So again, what we're doing is we're mapping the speed value. So you can think of this I as the speed value we're passing. We're going to map it based on the current I value from 0 to 100, our min and max, and we're going to map that to 0 to 270. So if you think about it as mapping from 0 to 100 and mapping it against 0 to 300, for every 1 mile per hour, we're moving 3 degrees. So 2, we would move 6 degrees, 3, we would move 9 degrees, and so on. Now, those numbers don't exactly work out because we're only going to 270, but essentially what we're doing is we're saying this is the range that we're expecting to input, and this is the range we want it to be. So we're mapping those values. Then we're taking that mapped value, its current position. So again, this is going to be based on whatever I value we're passing, if it's 0 or 5 or 99, or actually 98 because we're not going up to 99. But if we're passing those values, it's going to take that mapped value minus 270 and convert it to radians. So if we happen to pass 100, it's going to give us 270, which will make this portion 0. That cosine of 0 multiplied by the degree to radian value. Once we have those, then we can calculate the inside and outside points of that line. At this stage, now what we're going to do is we're filling the screen black, and then we're going to draw a line. The way that we draw a line is m5.lcd.drawLine. So pretty straightforward. We need to pass it, again, x and y0, x and y1, and then a color. So we're going to do x0, y0, x1, y1, and then whatever color we want. So I'm going to go ahead and use green for this just to make it different. And then we've got our gauge delay, and it's going to go back through and do the same thing over and over again. And again, the main difference between this and the reverse trip is simply the fact that we're going from 99 and down. So I'm just going to copy everything inside of there, including the map. And the only thing that's different is the I value we're passing is starting up at around 270 and coming back down to 0. So theoretically, this should now display our triangle, and then it should go and display our needle sweep. So let's go ahead and upload that and see what it looks like. And you can see that we have an error, and when we look at this, it's because I put a colon and not a semicolon there. So let's go ahead and just fix that. Let's try to upload again and see if we can get it to work. So everything there looks pretty good, but I think we can do a little bit better. So what I want to do is I want to create a filled circle in the center of this, and then I want to create another circle on the outside where we would expect the needle to be. So in order to do that, it can either happen directly inside of our sweep, or it can happen in another function. This is where you need to think about parsing out different bits and pieces of your function where it makes the most sense. So for us, what I'm going to do is fill the screen black, then I'm going to draw a filled circle. So m5.lcd. We're going to do fill circle and draw circle. So the first one I'm going to do is fill circle. And when we look at fill circle, you can see that we want x and y location, the radius, and the color. So the x and y location are going to be our x LOC, y LOC, and then the radius value we want is the inside. So that's going to be our gauge radius minus the gauge width. Again, this is where you could just program in inside and the outside radius. And the last thing that we need is a color. So we're using a green arrow. I'm going to go ahead and just say white for the inside. Again, semicolon. We're drawing the line, and then I'm going to draw the circle on the outside. The order doesn't necessarily matter unless they overlap. And instead of a fill circle, we're going to do a draw circle. We're going to use the X location, the Y location, and this time what we're going to be doing is the gauge radius. So if we want to make it a little bit bigger, we could add a couple pixels. So let's say add 2. Or if we want to make it thicker, then we can draw a couple of these and maybe do a blank out section before we draw the needle. Or we can simply just draw a couple circles of varying values. So what I'm going to do is I'm going to say gauge radius white. I'm going to copy that, and I'm just going to repeat it a couple times. but instead I'm going to just add a pixel each time. We're going to make the radius just a little bit larger. So on the return trip, if we want to sort of follow that same process, then we can just copy those values. And the draw line is exactly the same. So from the fill screen to the delay, I'm just going to go ahead and put those in there. Let's go ahead and save that. And if I didn't make any mistakes, we should be able to just upload that and see what it looks like. So you can kind of see that we get a little bit of a flashing that happens when we're drawing the gauge. And again, part of it could be because of the delay. Maybe we need more delay between it, maybe we need less. But what we're seeing here is that we're drawing the white over and over again, and then we're sort of blanking it out. So another way that we could think about this is every time we draw the line, we could redraw the line black so that it gets rid of it and we don't ever have to redraw the circles. So that's just another option that we could do outside of the for loop. So let's go ahead and give that a shot. So what I want to do is I want to draw the circles, and I'm going to go ahead and I'm going to bring all of this out. And then we're going to get rid of the line portion of it. So the line we don't need, that's going to be drawn each time. And then inside of here, we can get rid of the circle, the fill screen black. Another thing that you can do, so if you're playing around with code, you can just comment these out instead of getting rid of them. If you think you might go back to a previous version, you might want to leave some of that code in there. So I'm going to comment out the fill circle and the fill screen, the draw circle. And then what we want to do is we want to do the draw line. But after the draw line is created, I'm going to redraw this after the delay, except for I am going to draw it black, the same color as the background. And the same thing is going to happen down here. As we're erasing it, we're drawing it in a specific position, but I'm going to redraw it black. And after it finishes this line, it'll go back to the for loop, and it's going to just go back through the process. Now, this is probably not the best way. And I say probably not, it's definitely not the best way. But sometimes, depending on the graphics that you're choosing, simply redrawing over it the same color as the background and drawing the next iteration can be a little bit cleaner, because then you shouldn't get all the flashing. So let's go ahead and save this. Let's try to upload it and see if it looks a little bit different. So we can see that version is much cleaner. We don't have the flashing of the white on the black. The green line that we're drawing, you know, it has a little bit of flashing, but it's really not as noticeable as it was when we were drawing everything over and over again. So these are the kinds of things that it's good to test out. But remember that what we're doing here is we're sort of playing around with the graphics aspect of it to figure out the way in which we can create a gauge that we like. Now, ultimately, what we're going to be doing is displaying the speed number in the center and doing a swept arc. But hopefully this shows you that we can do the triangle sweep or the needle sweep a couple different ways. And this is going to be the basis, this foundation of finding these coordinates is going to be the way in which we progress to do the arc sweep. So I think at this point, let's make sure that we do save everything before we add the last gauge version and we move on to actually getting some GPS data. All right, so at this stage, we have our triangle that we're drawing, and then we have the needle that we're sweeping. The last bit of this gauge sort of design is going to be the version where we have an arc that's filling up, going all the way around, and then disappearing as we come back. I'm going to hop back into Paintbrush and just create a new design. And again, I'm going to zoom in so we can see this. Again, I think this is a good tool, at least getting started, to think about the geometry that you're creating, looking at it from a pixel perspective. So I'm going to create a circle. I'm going to go ahead and increase the size. Let's go ahead and let's just draw another circle and put it about in the center, and just think about what we're creating here. So at this point, we know the center, and we know that we can find the point. I'm going to go ahead and change the color. We know that we can find a point on the inside and the outside of this. The outside is the gauge radius, and the inside is the gauge radius minus the width. We're taking our the angle that we're sweeping. We are subtracting 270 to figure out where it is along this arc. We are then using cosine and sine to figure out the values that we can then apply to our inside and outside radius and the x and y position. So we can get this position and this position just fine. The next step in this process is to introduce a couple of more variables. We're going to introduce segments and increments. And the reason that we're doing this, we don't necessarily have to do this, but the reason that we are doing this is because we want to define two triangles. So if we're defining two triangles, we need 4 points. So we need to go a certain number of degrees. So for example, if we're going to go from here and we're going to go to here, let's say that this distance is 6 degrees. That's going to be our increment. And then inside of that increment, we determine how many segments we want to draw. So essentially what we're doing is let's go ahead and grab another color. We are going to draw triangles inside of these 4 points. And then we are going to fill them in. So they're going to be filled triangles. And again, I'll pick a different color. But this is the basic process. So we've already been able to figure out how to do the line part of that, which is just from one point to another, by finding this point here and this point here. So really the next bit is just some loops that we can use these new values, these increments and these segments, to figure out where the rest of those points are. And we're still going to do the same process. We are going to feed it those points, but instead of actually just plotting the line, we're going to plot everything from the start up into and including that line and the additional segments that go along with it. So we're going to just fill all of this stuff in for each value that we pass it. So that's going to be the important difference or distinction that we're going to have with our new program. So let's go ahead and hop back here and think about what we've already done and some of the values that we're going to need. So because we know what we did so far works, what I'm going to do is I'm going to copy everything with the exception of the draw circles. So I'm going to copy all this and just stick it inside of this arc sweep. Anything that we have commented out, I'm going to go ahead and just get rid of it. The fill circles and the fill screen, we're just going to get rid of those for now, just to clean things up so we can figure out what we actually need. And at the top of this, before the first for loop, we're going to define some new variables, and these new variables are going to be not global because they're defined just in the context of this. Now, we already know that we've got radius and width and x and y. Those are global. But we're going to define some new values for the segment and the increment. I'm going to call these byte because, again, when we use things like int or uint8_t, we are essentially reserving a certain amount of space in memory. If we use byte, then we have a very small bit of memory that we're using. So segment equals 6, and byte for the increment is equal to 6 as well. So again, we want to think about these as the number of segments in the increment and the width of these segments. You can play around with these values and increase or decrease them. So for example, if we make the segments 1 and the increments 12, theoretically we should get a bunch of spaced out sections. So it looks like it's drawing and filling these arcs, but it's leaving space in between. So now that we have these new variables, we are still going to have a for loop. We're still going from 0 to 99, and we are mapping that to 270. But we also have to think about the additional points we need, because at this point, all we have is the start and the end of our line. We don't have anything else. So let's go ahead and create some space between our map and these two float sx and sy variables that we created. So inside of here, what we're doing is we're creating this artificial loop, this for loop that is passing 0 to 98 miles per hour, and then we're mapping it to 0 to 270. Now, in the case of just the sweeping needle, it was fine because all we needed was the start and the end point. However, with the case of drawing each of these little sections of two triangles, what we actually need to do is another loop. So I want to take everything else that's inside of here. I'm going to hit Tab to space it in because I'm going to put it in another loop. So I'm going to say for int, I'm going to just call this j equals 0, and j is less than our arc map. And this is where it's going to get a little tricky. Our arc map plus our segment. And then what we're going to do is we're going to say j plus equals inc. So let's unpack that a little bit. But I also want to take this bracket and I want to move it after everything that happens in here, at least for right now. So we need to get rid of this extra bracket right there. All right, so let's look at what's happening. Right now, what we're doing is we're inside of this for loop, and this for loop is everything that's inside of here right now. So we're going from I equals 0 to 98 at one increment at a time. And then we're mapping that increment between 0 and 100 to 0 to 270, so we can pass it 0 for 0 or 270 if we happen to hit 100. So inside of that, every time that it goes through that I, it's then going into this for loop. So this for loop is starting at 0, which is the very basis, and it's going all the way up to the current value of ArcMap. So the current value of ArcMap plus our segment value, which is 6. So what's happening here is it's essentially saying the current value of ArcMap, let's say that we're going 5, the current value is going from 0 to 5, and it's filling that all in, plus that additional 6 degrees. So it's filling everything in up to that point, incrementing 6 degrees each time. So we're creating a 6-degree wedge, and then we're incrementing 6 degrees. So it's continuous as we go up. Again, if we change these numbers, if these are different, then you'll notice that we'll start to see spaces in between each of those bars. So at this stage, now we're inside of another for loop that's going through. And the j value in this instance is important because now what we're doing is we're taking this j value, which is going from 0 to ArcMap. So our ArcMap value inside of here is no longer valid. So we really need to pass it something else. So what we're going to be doing is we're going to be replacing that ArcMap with this j value. And then as we go through the other values, we also need to calculate a few more. So at this point, remember, we've only really looked at creating the start and the end point of a line. Now, we've got 2 x coordinates and 2 y coordinates. Now, we need at least 3 to make our triangle, and ideally we want 4 so we can build those 2 paired triangles to sort of fill in that little wedge. So we need to make some more floats. So float, it's going to be sx2, and that's going to be equal to cosine, and this time it's going to be j plus our segment minus 270. And then that's going to be multiplied by degree to radian, just like before. Remember, the capitalization matters. We're going to do the same thing for sy2, and this one's going to be equal to sine j plus segment minus 270, and we're going to multiply that by degree to radian. So what we've essentially done is up here, we figured out where the actual points on an x and y for the start and the end point of what was our line. Here, we're doing the exact same thing. We're just incrementing it another 6 degrees. So if this j was at 45 degrees, this one's going to be at 51 degrees. It gives us our 6-degree wedge that we're building. But with that, now we need to get x2 and x3 that correspond with those values. So again, we're going to do int, we're going to do x2, and this is going to be equal to sx2, because before we did just sx, and that's going to be multiplied by our gauge radius, we're still using those same values, minus our gauge width, plus our x location. And make sure that we do use the correct semicolon. And then int y2 is going to be equal to sy2 multiplied by our gauge radius again, minus our gauge width. And we're going to add our y location. So that gives us 2 more points. We can now build one triangle, but we need that last point that is going to be on the outside radius. So this one here, gauge rad minus gauge width, that was on the inside. So let's go ahead and do an x and y3. Int x3 is equal to sx times, in this case, it doesn't have to be in brackets, but I'm going to go ahead and do it just for consistency, plus our x location. And the same thing for y. y3 is going to be equal to sy3 multiplied by our gauge radius, and that is going to be plus our y location. So this now gives us everything we need to fill that in. Remember, we don't really need the lines, so I'm going to go ahead and get rid of the lines here. But I am going to go ahead and space this down just to make a little bit more room. Now is the point where we can create our filled triangles. So m5.lcd.fill triangle, and we're going to go from x0, y0 to x1, y1 to x2, y2. And then we need to give it a color, blue. We're going to do the same thing again. Of course, you can copy and paste, but I'm just going to go ahead and type these, triangle. And now we're going to be going from x1, y1 to x2, y2 to x3, y3. Now, remember, we are sharing some of these points, and that's how we're getting that wedge shape, because we're going from 0 and 1, which was originally defining our first line, to x2, y2. And x2, y2 is building out that little piece that is on the inside of our gauge, because we're doing gauge radius minus gauge width. So we went from this point here to this point back down to the inside radius. Then our next triangle is going from x1, which is that point on the outside radius in line with our current location, x2, which is that inside point, and then x3, which is the outside point at the end of our 6-degree wedge. So we should be able to build that, and keeping in mind that all of this is happening inside of a loop. So if we take a look at this last bracket, everything from this bracket is happening inside of this for loop. So each time we go through one iteration of the speed, in this case 0, 1, 2, 3, and so on, we're mapping that, and then we're passing that mapped value in as a condition for our next for loop. So it's going to start drawing these wedges all the way up to and including that. Now there's one last bit of this that we need to do before we finish. So let's go ahead and add a little bit of space. Because we want to build these segments each time we go through, we need to store some of these values as the starting point for the next time through. So what we're going to do is we're going to say x0 is equal to x2. Then we're going to say y0 is equal to y2. Then we're going to say x1 is equal to x3. And then y1 is equal to y3. Now, theoretically, this all should work fine. We are copying these values, and theoretically, this step should not be needed, because what we're doing is we're recalculating it each time with the current speed. However, if you were only calculating the second point, if you were expecting to build this up linearly, then this step would be required so that you can remember that last coordinate point. I don't think this is needed, so I'm going to use Control and Slash and comment it out. And then we're going to take a look at what happens here. Keeping in mind that we haven't done anything for the return trip yet. So this entire for loop, I'm going to hold down Control and hit Slash to comment it all out. We should see that this goes to our for loop here. This one goes to this for loop, and this should be the end of our arc sweep function. So let's go ahead and save this. Let's verify it, which again, verification happens whenever you actually try to upload to your, in this case, the M5Stack. But what we're going to do is we're going to just try to verify it first. You can see we got a problem. SY3, it says, is not declared in this scope. And that's because that should be a 2 and not a 3. So SY2, that caught that error for us. I'm going to go ahead and upload this, and let's take a look to see what happens. Now, you can see that it's working, but two things are happening. One, we still have the white circles that were left behind from the last gauge. And that's because we never refilled the screen. It's still going back and it's still referencing everything that was done before it. So a good way to sort of fix this is for us to take this fill black screen and we can stick it somewhere in the code, because remember, we're redrawing this each time we go through a different I value. So each time we go through a different I value, theoretically, we should be able to fill the screen here. The second thing that's happening is we've got a delay in here. And the delay is happening after we create this triangle. But the problem is, this is a for loop that's inside of another loop. So I'm going to comment out the delay. I'm going to go ahead and resave this. And I'm going to re-upload it. And theoretically, it should speed up now. The white circles should be gone. And we should now be clearing the screen. And it should make things go a little bit faster. So we can see that that's happening quite a bit faster now. Because we do have the black screen and we don't have any delay anywhere, we are getting a little bit of flickering. We could go ahead and add in a small delay. So I might use gauge delay in here just to slow things down a little bit, but everything seems to be working fine. Of course, we didn't need this bit, so I can go ahead and get rid of it. But remember that if you are expecting to actually recalculate the last point, then you would need to store that in some way. The last bit that we need to do is we need to reverse everything that we did. So I'm going to uncomment this out, Control Slash, but I don't want to keep any of the stuff that's inside of here. So I'm going to get rid of it all, and I'm just going to simply copy everything up to and including everything inside of this for loop. So I need to make sure that I have the right number of brackets. So what I want to do is I want to find where the bracket is for this for loop, because that is going to be this bracket here. And I'm going to go ahead and copy everything up into including the arc map. So inside of here, I'm going to go ahead and put all that in. And theoretically, we should be wiping the screen each time. And we should be calculating the exact same values. The only difference is now we're passing the I values starting high and going low. And also to speed this up, what I'm going to do is I'm going to go back to the original void loop. And I'm going to comment out try sweep, this delay, needle sweep, and this delay. So the only thing that we're looking at is arc sweep. So I'm going to save that and go ahead and upload it so we can take a look. So we can still see that there's quite a lot of flickering that's happening. And part of the reason that there's a lot of flickering is because, again, what we're doing is we're wiping the entire screen and we're redrawing everything over and over again. So if you're having this issue, a couple of things that we can think about. One is where we're filling the screen and if we actually need to fill the entire screen or not. So we are drawing filled circles right now. And essentially we're drawing filled circles. But what we're doing in essence is we can create a filled circle that's black. That's exactly the size of what we need to blank out. That could be a way that we could do this. Or we can think about whether or not we need to clear it. So for example, as we're increasing, We don't ever need to clear the gauge because the value is always getting bigger. And if we're decreasing, we need to clear it every time. So this means that I can get rid of the fill screen on the increments that are going up, and on the ones that are coming down, I'm going to take the delay out, just comment it out, but I do need to either fill the screen or I need to draw a black circle to blank out what's already there. So instead of filling the entire screen, which depending on the size of your gauge might not make a whole lot of sense, what we could do is we could do m5.lcd.fill_circle. And remember, we're looking for the XY position, which is going to be our X location, our Y location, our gauge rad for a radius, and the color. And again, if you forget that, the .h file or any of the help files that are associated with whatever library you're using, if you're not using an M5Stack, you're using something like an Adafruit GFX library, then there are tons of resources on what values that you need to use. But for us, fill circle is looking for X, Y, radius, and color. So this should alleviate some of the flickering on the going up. And also think about the fact that for an actual gauge, you're not going to be constantly incrementing. Theoretically, you're going to have it increase to a certain point, and then it's going to sort of stay there, and it's going to go up and down a little bit, but we're not going to have to deal with this constant flickering. Also, we're not going to be looping through these entire values. We're going to be passing it a speed, dealing with that, and then displaying that for a certain amount of time. So let's go ahead and save this. Let's look at it one more time. So now we can see the increase is a whole lot smoother because we're not blanking out the entire screen and redrawing the blue in rapid succession. The decrease is still minimizing it. And again, some ways that we could think about this is if the speed is decreasing, instead of us going through and blanking out the entire screen, what we could do is take our last known speed and store it, and then we could just simply redraw those two triangles for that 6-degree segment as black instead of blue and take it away one segment at a time. So in reality, if you're just doing a demo screen, that is a much cleaner way. You don't get the flicker. However, when we're talking about doing it and passing randomized speeds from GPS, it does have its own set of problems. You're going to need to think about if the speed decreases, if it drops rapidly, let's say you slam on the brakes and you go from 50 to 20 rapidly, well, you need to be able to account for that 30 mile per hour drop. You can't just instantly jump down to 20 and start clearing it away because then the segment is left behind between 20 and 50 miles an hour. So you have to be able to store the last value and you have to wipe away those values. And you can store them in a buffer or in an array and sort of clear them and reassign them every once in a while. That's certainly possible. But again, the logic that goes along with that takes a little bit more time to plan. So we're really trying to focus on understanding, in this case, the math behind the graphics on how to make this work. But also we want to understand where potential deviations in the process lie, because sometimes you go down a certain path and there'll be a performance benefit, but it'll be a negative in another area. Sometimes you'll go down a path and the performance will suffer, but it'll be a positive in another area. So for us, I think we're at a pretty good spot. I can go back and I can uncomment some of the other gauges that we did. Now, if you want to continue to play around, and if you do have an M5Stack, or if you have some buttons, then you could go through and you could, inside of your loop, you could do some conditional statements that say, you know, if you press a button or if a button is released, then go to try sweep. If you press a button and it's released, go to needle sweep and so on. Because I'm going to assume the majority of people are not on an M5Stack, I don't really want to continue to go down that development road, but it is fairly easy to do. So at this point, let's do a quick recap on what we have and what we're going to do from here. So we've explored the graphics for 3 different styles of gauges. The tri-sweep, which is just the increasing triangle wedge. We did the needle sweep, which we drew a filled circle in the center, a gauge around the outside, and we're drawing the line and erasing it each time. And then we did the arc sweep, which again was by far the most complicated, but it followed the same process of doing the needle sweep because we had to find the X and Y locations at the current speed. But then we also incremented it 6 degrees. And with that 6 degrees, we found 2 more points, which would make 2 sets of triangles. With all that said, at this point, now we have covered the graphics aspect. We've talked about for loops and if statements. And actually, we really haven't done any conditional if statements, but for loops are really all we've needed so far. We've created custom functions and we've looked at graphics and text. So those are the basics that we need. The next step is going to be GPS software. So what I'm going to do is I'm going to save this program, but we're going to create a brand new program, and we're going to talk about GPS, and we're going to talk about the way in which we can access. There's a lot of different libraries and ways that you can do GPS. Some are easier than others, so these are going to be important considerations. So let's go ahead and make sure that our program's saved there now that we've got the graphics aspect of it done, and let's hop into doing some GPS. Now, with GPS, there are a couple of important things that we need to know. One, you will need to have a GPS library installed. There are plenty of different ones that you can use. Tiny GPS and Tiny GPS++ are probably the most user-friendly ones that you can come across. And there are examples if you go inside of the examples library, depending on which one you're going to use. So for example, I'm going to be using the Tiny GPS++, but you can go into whichever library you're going to use and you can find examples. So for example, this one here, we've got full example kitchen sink, which that is essentially every code or command that you can use. There's a basic example, device, custom fields, and so on. So in order to get a library, you'll need to find one. Now, the Tiny GPS++ has been updated and is really easy to use, and I would suggest that you use this one. This is the one I'm going to be using. It doesn't mean that you have to use this. And again, if you go to GPS modules, like if you happen to be using M5Stack, there are learning sections. So you can see there are already some. Here's a GPS tracker with documentation. These ones are likely going to be quite a bit more involved than what we're doing. So once you have a basic understanding of dealing with the GPS data, then by all means you can dive into some of these projects. There are, again, other resources that will help you learn that, but the documentation in the library that you use a lot of times is kind of up to you. So the reason I like the Tiny GPS++ is it handles a lot of the back-end information and parsing that typically is something that you need to do in the code. So for example, there are the NMEA sentences are the way in which you communicate with the satellite data. The Tiny GPS++ takes care of all that for you by using commands like gps.location.lat and gps.location.long. Where in the past you would have to essentially query the information that you want from the satellite, and then you'd have to parse it out based on the way in which it was sent back to you. So this right here is a typical sentence that you would get back. So it tells you things like the elevation, the lat and long, potential direction you're heading, west, for example, speed data, and so on. So it would pass all that back to you, and then in your code, what you'd have to do is you'd have to sort of dissect that based on the position of the information that you were looking for. So for example, if you wanted to know the speed, then you would have to parse out the speed based on where it was relative to each other bit of information. Now, where this gets really tricky is when information starts getting dropped or you don't have good data to start with. So again, the Tiny GPS++ is a really easy to use library. There are other libraries out there that you can use, maybe have more functionality, but this one is really user friendly. So for an example like ours, we're really looking at just pulling out data about maybe lat and long and maybe speed. It's a really great option. So the first thing that I want to do is I want to start a new program, and I want to talk a little bit about the setup of the GPS antenna, because depending on what you have, obviously your setup is potentially very different from mine. I'm using, again, the M5Stack gray. The gray is no longer available, but generally all of the M5 stacks will have very similar results. I'm using the GPS module that they have, the AT6588, which we looked at in the first video. And this is a UART communication, and this is typical of what you would find. Now, the problem with the M5 stack that I have is that the groove connector is not UART, it's I2C. So that means I can't just plug this in and it works. If you happen to get the stack module where you plug it in, then yours should just work fine. Or if you're wiring up something else, if you have a GPS shield from Adafruit or SparkFun, then you're going to want to make sure that you configure those pins. Now, for me, what I'm going to be doing is I'm going to have pound include, and I want to make sure that I have my M5Stack.h library. And then I'm also going to do a pound include, and I'm going to be using the tiny GPS ++.h. So with those two libraries, I will be able to communicate with the M5 stack. I can display stuff on the screen. I can have the speaker beep. I can do whatever I need to. And I also can communicate with my GPS antenna. There is a bit more that has to happen with that. And there's a couple other things that we need to understand. So the first thing I'm going to do, and this is going to be standard, is define what the baud rate is to communicate with your GPS modem or your GPS sensor. And this information is going to be generally 9600, but if you're using some sort of off-the-shelf U-Blox GPS sensor that is looking for a different communication rate, then that's something that you need to look up. But for us, with this specific unit and other units that I've used, it's going to be static const. We're going to do uint, and if I can type, uint32_t. And I'm going to set this as my GPS baud, and it's going to be equal to 9600. And again, there are examples. If you're using the tiny GPS++, you can go to the examples. We can go down here and we can do a basic example, and it shows you, including the library. Here is a sample stream of GPS data. So this is what's coming in and this is what it's parsing out. You can see that they're using a different serial amount, a different baud rate to communicate. And then they're sort of pulling out data. So again, this is a sample stream. This is happening in the back end. We don't really have to worry about that with this library. And we are just calling different bits of information. So again, at the very basic level, all we really need to get is speed, which is looking at the current position of our GPS antenna relative to its last position with all of the different satellites it's getting. The next thing that we need to define is the object associated with tiny GPS. So the way that we do that is we set up our tiny GPS plus, and we're going to set it up as just lowercase GPS. Next, we need to start or initiate the software serial connection. Now, the way that the serial communication works is different for different boards. So sometimes you might have a specific microcontroller that can do true hardware serial communication. Sometimes you might have to do like a virtual or a spoof of it. For us, on most Arduinos and on this unit, what we're going to be doing is we're going to be doing hardware serial SS, and in the brackets, we're going to do a 2. So the SS is going to be how we start communicating with our antenna, and we're going to do that by using this GPS baud rate. Now, some of the stuff that we're defining here is not really going to make much sense if you're not really going to get into GPS parsing and working with GPS on the back end, and all you really want to do is get lat and long and speed, then just use the data that is associated with examples that work for you. That's kind of my suggestion. If you don't have to know everything about GPS, then don't worry about it. Inside of the setup, what we need to do is we're going to start the M5Stack, so m5.begin. Again, if you're using an Arduino, then this is not something you need to do, but for us, we need to do power.begin. Again, we're going to allow it to run off the battery if it's not connected via the USB cable. And then we're going to take our software serial.begin, and it's looking for a couple of different bits of information. So we're going to be doing GPS baud. It's looking for the communication rate. And then the next bit of information is going to be something that you'd have to look up on a chart. So it's going to be serial underscore 8N1. And then I need to define the pins for receiving and transmitting. And for me, that's 16 and 17. For the M5Stacks, that's what it's going to be. If we go ahead and hop back over to the GPS modules, so this one here, you can see that the baud rate is 9600. That's what it's expecting. So that's where I got the 9600 value, is because that's what this GPS is looking for. I can also see that the wiring is looking for transmit and receive, TXD and RXD, then 5 volts and ground. So wiring this up, even if it doesn't plug directly into the groove connector, is pretty straightforward because I can take the TX and the RX and take them to pins 16 and 17. As we look down through the rest of the data, you can see that they give you a tiny GPS++ library. So that's a related link. That's one of the ones that they want you to use. There's some bootloader data here, and there's more GPS data. So you can see that using something like UI flow, pretty straightforward. UI flow is pretty handy for sort of a visual learning process for coding. It's not necessarily required, but it can be pretty nice for you to build out things like labels and have them put in a certain location. You can see that it's some examples of data. It's spitting out lat and long, and there's some support information here. When we're looking for information about what the software serial begin is, the best way to do that is to search through the Arduino documentation. So I'm going to do .begin. And as I'm looking through here, you can see there's a serial begin. And if I click on that, then you can see that there are some serial port objects. The serial underscore 8N1, this is the default. This will vary depending on which board you are using. Certain boards will require certain things. You can see here that software serial.begin, it's looking for speed and configuration. So we're passing it 9600, which is our GPS baud, and we're passing it the serial 8N1 as our configuration. It's also looking for 2 additional objects for us. It's looking for the pins for communication. And again, that is going to be dependent upon which device you actually have. When we're talking specifically about UART connections for the M5Stacks, that's going to be pin 16 and pin 17. So these are just things that you need to be aware of. This unit here, as they note, if you're using it on an M5Stack Fire, you will need to do some jumpers to different pins because 16 and 17 are already taken. But again, they show you the default baud rate for the protocol, 9600. It's 8 bits, 1 bit is to start, 1 bit's to stop. And they're using 17 for receiving and 16 for transmitting. So with all that out of the way, now we have the basic definition. And again, if you're not planning on going super deep into what's actually happening, just sort of take this at face value. Some cases, you might need a different baud rate, you might need a different serial configuration. It's going to be really dependent upon what equipment you're using, which is again why I strongly urge that you purchase equipment from somewhere that has a resource like Adafruit or SparkFun. Anytime they have a GPS module, they will have examples on how to use it. A lot of times they will write their own libraries, or they will point you to the library that they use in their examples. And it just takes a lot of the work out of it. You don't have to figure these things out. But at this stage in the game, this is all that we need to set up the GPS antenna. So at this point now, we've started communication. We've started the M5Stack. We've told it that it can run off the battery. Now inside of the loop, this is where we want to begin pulling information from. So inside of here, we're going to use what's called a while loop. So we're going to do while, and in brackets, SS, software serial available. So essentially while we're communicating, and again, we're going to put the closed brackets, is greater than 0. So while software serial is available and we're actually receiving something, we're going to do gps.encode ss.read, close the brackets off, and a semicolon. So now essentially what we're saying is that while we're communicating with the GPS antenna, we want to read that. And again, if you make any text errors, you'll notice that some of this stuff doesn't change colors. It should be gps.encode and ss.read. And again, things like software serial begin and encode and available, it's really best to pull these out of examples, and examples from the tiny GPS++ will tell you exactly the bits of code that you need to get things running. Unless you're trying to dive deeper into parsing out your own NMEA sentences that come back from satellites, then I would stick with some of the examples. From here, the only thing that we really need to do is display the speed. Now, I'm sitting still at my desk, so my speed is going to be 0, but you can parse out the lat and the long and the speed just by simply calling those. So what I'm going to do is I'm going to say m5.lcd.set text size at 3, and then I'm going to set the cursor, m5.lcd.set cursor, and I'm going to put it at 1 and 100, so just down the screen a bit. And then I want to print m5.lcd.print miles per hour. Also remember that we can do printf and print line. Print ln will print on the next line. And then what I'm going to do is I am going to set my cursor again, m5.lcd.set cursor, and I want to move the cursor over a bit. So we're going to move it over from 100 to 100. So we're going to set it at 100. So it should be in line, just moved over to the right. And then we're going to print out the speed. m5.lcd.print gps.speed, and then we tell it we want it in miles per hour or kilometers per hour, whatever the units are that you want, as long as the library supports that. And the beauty of this is that this is all we need. We now have a GPS speedometer. It was really that easy. We didn't have to go through all the trouble of all of the graphical stuff that we were trying to do. However, this is boring because it's just going to be a number displayed on the screen. But let's go ahead, let's save this. I'm going to go ahead and call this lead GPS num. And I'm going to go ahead and upload it. So we're going to upload it and we're going to take a look to see what this looks like. And there we go. So you can see that just by moving the GPS antenna, even though I'm inside, moving it around on my desk just a little bit, was able to register a number. Now, by default, miles per hour will come in with 2 decimal points of precision. You can also query other data. So for example, we could do m5.lcd.print gps.location.lat, and then we would tell it that we want 6 decimal places. And that would just print out the latitude or the longitude if you did location.lon, or I'm sorry, location.lng, and it would be able to print out that information. So pretty straightforward to get that GPS information, assuming that you have a product, in this case the M5Stack, something that actually has some data behind it. Now, again, I really like the M5 line of products just because they are so simple and they already include the screen, the buttons, the speaker, the SD card. Mine has the 9-axis IMU. So with the external GPS antenna, I can now record things like acceleration and deceleration, lateral G's and turns. I can record elevation with the GPS, and I can record current speed, lat and long, the direction that I'm traveling. So north, south, east, and west. I can pull all of that data directly from the M5Stack's internal unit as well as this external GPS sensor. The next thing for us to do is sort of put all of that together. Remember, we had this list of things that we wanted to accomplish. The graphics, which we've done the easy, display a number, display a bar, display a filling arc. We did the basics of for loops. We didn't really handle any if statements. That was going to come more in if you include the buttons, but the logic still stands. We understand loops. We understand how to create functions, do basic graphics. We now are able to do our software serial connection and how to initialize and read the data and display it. Again, the buttons are not really important, especially if you're not using the M5Stack, so we're going to skip that part. But the last is for us to understand what is happening with the flow of data, which means that we need to make one more program to combine everything that we learned. So make sure that you saved what you've done so far. We're going to combine the GPS data, and we're going to combine our intro play, which has our different screens. We are going to configure some of it, but we're going to put it all together. So in order to put all of this together, what we want to do is we want to copy the gauge style that we want, and we want to sort of incorporate all of that, including displaying the speed in the center of the gauge along with the GPS data. So to do that, we're going to create a new program. I'm just going to stick it right here in the middle so we can copy and paste everything that we've done so far. So with our new program, let's go to the top of the original program. I'm going to make some space in here, and I'm going to bring in everything from the top. The pound include of the M5Stack, and I'm going to bring in the degree to radians, all the values that we configured. I also want to bring in my tiny GPS++, and this is part of the reason why I like tackling these projects a little bit at a time. Now, in reality, what we ended up doing was we put all of the different gauges and all that stuff into one program, or sketch as Arduino calls it. But in reality, I probably would have done that in 5 or 6 different ones. I would have printed the GPS speed, I would have figured out what I want the gauge to look like, and then sort of worked on combining them all together. But at this stage, what we can do is we can start to just copy everything that we know works. So I'm going to do the GPS baud rate. I'm going to bring in the tiny GPS plus object, hardware serial, software serial item, and then all of our constants that we defined. Inside of our setup, we need to do the software serial begin. So inside of here, I'm just going to bring that in. And then over here in our setup, we originally printed M5 test graphics. That's not something that we really needed, but if you want just a visual display that something is happening at startup, then you can certainly put that information in. Sometimes it is nice to have a little bit of a delay at the beginning after you start the software serial, just simply because it gives it time to communicate with any sensors or any of the peripherals that you're using. So if you want to include that, you certainly can, but the main things for us are going to be begin and power begin. And we also want to make sure that we start the software serial. So that's communicating. It's on pin 16 and 17 for me. Again, if you're using an M5, those are going to be the pins, unless you happen to have one with the groove port that has UART on it and not I2C. So now inside of our loop, this is where we need to think about what's going on. Um, Now, generally, when you start a vehicle, at least any modern vehicle, the gauges will actually sweep the needle and go through to sort of show you that it's working. So if we want to include that, then we can build out our own function that just sort of sweeps through some values. But the main thing, I mean, at this point, I don't know how many hours we've been at this, but at this point, really, we have all the bits and pieces. We've already swept through in some of the other programs. So really what we just need to do is we just need to get in. And what I want to do is I want to do a fill screen to at least make sure that the screen is nice and clean. And inside of my setup, what we want to make sure that we do have is, again, power begin and M5 begin. We want to make sure that we're communicating with the correct baud rate, the correct serial protocol, and the correct pins. And then if we want to sweep the gauge, we can. Inside of the loop, what we're going to be doing is the while loop. While the software serial is available, GPS encode and read. So that way we're pulling out that information. Where things start to differ for us is that now what we're going to be doing is we're going to be passing data from our loop into a program that's going to build out the gauge. So we're going to start to build out functions that do different things. And then what we are going to end up doing is passing variables. That's something that we really haven't done yet. We talked about it very early on, but we haven't actually done it. So I'm going to define some variables, and they're not going to be constants because they're going to change, but I want to define an int as my current speed, so CUR speed. I'm going to set that as 0 just initially, and an int for my last speed, LA speed, and I'm going to set that equal to 0. So those two values are initial values that are sort of placeholders. Then inside of my loop, what I'm going to say is my last speed, or LA speed, is equal to my current speed. So the first time that it goes through the loop, it's going to say, okay, well, last speed is 0. It equals current speed is 0. It's pulling out whatever that value is. After I set my last speed, I'm going to have a little bit of a delay in here. And the main reason I'm going to have a little bit of a delay is because what I want to happen is I want to have a small delay between when I read the current speed and when I do something. So 125 is an eighth of a second, a very minimal display. We can shorten it or lengthen it if we need to, but for right now, I'm just going to sort of slow the process down. And then I'm going to say my current speed, CUR speed, is equal to gps.speed.miles per hour. And in our example, that's exactly what we just printed to the screen. But now I'm taking that value and setting it into this current speed variable, which was 0, but now it actually contains the GPS speed. From here, what I'm going to do is I'm going to call to a function. I'm going to say, all right, well, now that I have my speed, I'm going to send that information to a function that's going to actually do something. I'm going to call this arc with speed. Now, if you want your gauge to just have the needle or the triangle, then you can certainly do that. I'm going to continue on with the hardest one because we put in the most work to make sure that that worked. So what I'm going to do is arc with speed, and I am going to pass some values to it. So I'm going to pass the current speed that we just pulled from the GPS as well as the last speed. The reason that that's important is because the current speed just got pulled from the GPS. However, the last speed, the first time around, was 0, but after it runs this arc with speed function, it's going to come back to the loop, check the GPS, the software serial again, get another reading from the satellites, and then it's going to say, okay, well, the last speed was equal to the current speed, but then it's going to reset the current speed at whatever our GPS says. So this is a good way for us to sort of maintain the current speed and also fill or save that last speed in each time we go through the loop. And we have that small delay between them, gives us a chance to make sure that they're different enough before we act on the gauge. So now that we have that, we need to build out our program, our function that's going to start doing something. So we're going to say void arc with speed, and the arc with speed is going to have to accept two values. So we're going to accept an integer current speed and another integer last speed. So initially what I did was I just called them CUR speed and LA speed, but inside of here, I'm going to redefine them as something else. Now, if they were done globally, like they were up here, we would want to make sure that we're really careful about their definitions. I could define those in the setup, which only happens once, and then they would not be available inside of the loop because I'm not passing anything to. I could define them in the loop, but then what's happening in the loop is it's going to get reset to 0 each time. So I have to be real careful where I put some of this stuff and whether or not I'm changing it. I don't want to change it, so I'm going to just create new variables, current speed and last speed. Then I need to do my curly braces, and that's going to start to define the program area. I'm just going to build out a little bit of space here. So inside of here, what I want to do is I want to call up another program that is going to draw the gauge for me. And then I want to call the program that is going to fill in the arc. And the reason that I want to do it this way is, again, we can sort of parse out each piece of our project. It doesn't all have to happen at the same time. There are benefits, certain projects, to doing them separately. So we're going to create another function called drawGauge, and we're going to pass it the current speed. Now the gauge is going to be just the numbers. So I'm going to add a comment here. This will draw just the number and MPH. So that way I know that I'm passing it the current speed. Now, what I want to do is I want to map my current speed to my 0 to 270 degree arc. So before I wanted to pass it to the function that drew the gauge. So I have the current speed, but then I now want to map it. So we're going to create another variable, int current CUR speed U for speed update. You could call it speed map or whatever you want. And this is going to be mapped to our current speed. So this current speed that we are just passing it directly from the GPS, our minimum speed, which is 0, our max speed, which is 100, and then we're going to map it between 0 and 270. You can always go back up and make sure those values are right, min speed, max speed. And then now we're going to call up our routine. Now in our case, the original routine we called arc sweep. So I'm going to just call that arc sweep again, but this time we're not just calling it and running through some empty loop. What we're actually going to be doing is we're going to be passing it some variables. So we're going to be passing it the X location, the Y location. We're going to pass current speed U, and that's going to be our value from 0 to 270. We're going to pass a number 1, and we'll explain that in just a minute. We're going to pass our gauge rad, our gauge radius, and we're going to pass our gauge width and the color we want it to actually create. Now I am going to come back up here and I'm going to reduce this gauge width to 30, make it a bit thinner, because we are going to display some numbers in the center. Actually, you know what? Let's make it 20, make it a little bit smaller. All right, so that's all that has to happen in this arc with sweep. We've passed it the current speed and the last speed. Notice that we didn't actually use the last speed. It's in there just in case. And the reason I say just in case is because if you want to do some conditioning, such as an if statement to see if the current speed is greater than the last speed, then you could do it in this function because we passed both. We don't actually need to do it right now, but if we were going to create a gauge where, let's say that we were going to store that last speed and decide whether or not we're going to wipe the entire gauge or just part of it, those would be options for us. Now we need to come up with this arc sweep and this draw gauge. So let's start with draw gauge, and keeping in mind that draw gauge is looking to be passed a value, its current speed. So I'm going to create an integer and I'm just going to call it speed. We're going to close the brackets and then we're going to do some open curly braces, and that's going to build out that little section. So a lot's going to happen in the draw gauge. We're going to do m5.lcd.fill circle, and this is going to be our X location, our Y location, as well as our radius value. Now, this is actually going to be a circle that is used to wipe out everything that is there. So remember that our current radius is 90, it's gauge radius. So we're going to be looking at our gauge rad, but we want to add a little bit to make sure that we wipe everything. So I'm going to add 2 pixels to it, and then we're going to do this as black. So that first step is wiping everything that's on the screen, at least within that 92 pixel radius circle. Then what we're going to be doing is drawing some circles. So m5.lcd.draw circle. And this is going to be our X location, Y location, which is going to be the center of everything. And then what we're going to be doing is drawing circles on the inside and the outside bounds of where we want that arc to sort of fill in. Kind of like in Paintbrush here where I drew circles on the inside and outside. We're going to draw those circles. So what we need is our gauge radius. We're going to subtract the gauge width. And if you forget what these values are, you can always just scroll up. Gauge width, it's 90 for the radius, 20 for the width. So now we're at a 70 millimeter radius for the circle. If we want it to be a little bit bigger or a little bit smaller, we can also add or subtract, again, a pixel, and then decide what color it's going to be. I'm going to make this one red. And then we're going to repeat that draw circle several times. So what I'm going to do is I'm going to take this and I'm just going to copy it. So we're going to draw one that's at 90 pixels. We're going to draw one that's at 72 and 91. So I'm going to go ahead and just bring those back for formatting. And again, the formatting is really a visual thing. So we're going to have one at 71 and 72. And then we're going to have one at 90 and 91. So 90 was our gauge radius, and 91 is going to be our gauge radius plus 1. Remember up here we did the original black circle, which was 92, which wiped everything out, just with a 1 pixel border to make sure nothing was left behind. The reason that's important is because we are dealing with pixels and not true arcs. So the pixels could tend to bleed over if you try to make them the exact same size. So now what we've done is we've blanked out the center screen and we've drawn red circles on the inside and the outside of where the fill is going to go, and those are 2 pixels wide. So the next thing that we're going to do is we're going to set where the speed actually is. So m5.lcd.set cursor. And this one's a little bit tricky. So the M5 has parameters where we can do centered text, but I don't think most of the graphics or the libraries do have that. So I'm just going to do it based on the corner. So I'm going to set my cursor at 120 by 95. And then I'm going to set the text color. Now, by default, the text color is going to be white, but it's always a good idea to actually intentionally set it. So set text color, and I'm just going to use white. Just keep in mind that we're using just some of the standard colors that are already enabled. If you don't have those enabled, you can define colors in different ways. But for us, I'm just going to use some of these standard colors. I'm also going to set the text size to be fairly large. m5.lcd.set text size, and this is going to be 7. And the reason I'm doing that is because we want it to be large enough to see. These are small displays, again, about 2 inches. And having small text is going to be very difficult to read, especially if there's any sunlight. Now, I don't really have any intention of using this program on this specific gauge. In reality, this is just sort of a development process. So now that the text is set, what we can do is we can do m5.lcd.print, and we can just print the speed. Now, speed is what we passed into this routine. Now remember, we're not expecting anything to come back because we're using void, but we still can pass variables. We can draw everything we need to with those variables, and then we can hop back into that previous program. So now that we've printed the speed, the other thing I want to do is just print miles per hour or kph underneath it. So m5.lcd.setCursor, I need to tell it where that cursor needs to be. For this, I'm going to put it at 140 by 160, and then I'm going to set the size to be smaller. m5.lcd.setTextSize, and I'm going to make this a 2. And last, we're just going to print out the words miles per hour, mph. So we're going to print in double quotes, mph, all caps. And then if you want to, you can include a delay. So I'm not going to put a delay in here, but basically what's happening is inside of our arc with sweep, what we're doing is we're calling draw gauge, and we're sending it current speed, which is the value that we pulled directly from the GPS antenna. We're passing that directly to draw the gauge, which is wiping everything out first. It's drawing a double wide red border on the inside and the outside of where the sweep or the arc is going to go. And then it's displaying the speed as 7 size text and then miles per hour underneath it. Now you could also put some of this text outside of this circle that's blanking everything out and not have to refresh it. But honestly, it's already getting refreshed with the speed, so you're not going to notice any additional flickering or anything that happens from this. But now that we've drawn the gauge, the next thing that we need to do is notice that it's going to go back, and then it's going to map the current speed u, and then it's going to call this arc sweep x location, y location, current speed, this one random value that I tossed in, gauge radius, gauge width, and the color. So let's go ahead and let's build out what is actually happening with this. So we're going to do a void again. And also I forgot to put void up here before draw gauge, so let's make sure that that's included. Void arc sweep. Now, the arc sweep that we did over here was something where we included all of the variables directly inside of the program. Now, we could do that again, but the whole intent of this is to pull in the GPS speed in the loop and pass it along to where it needs to go. So this is going to have to receive some variables where in our test, all we did was just make them up and automatically sweep from 0 to 100. So inside of our program here, and again, void when we're defining this function is okay as long as we're not expecting to return something. But what we're going to be doing is we're going to be defining some variables. So we're going to do int x, int y. These are x and y locations, keeping in mind that we are passing it some variables. We're passing x location and y location already. We're going to pass in current speed, and I'm going to use an underscore here. We're going to pass in that random value, that number 1 I tossed in there. So what this is this is a segment count. Now we already talked about segments and increments in our arc sweep. The segment count is another variable that we could configure to sort of change the way in which the gauge works. Now, when we talked about segment and increment, I mentioned that if they're different, then you end up creating little spaces between, and the increment kind of, or the segment count kind of has that same effect. Then we're going to pass in an int for the radius, an int for the width, and then we are passing in the color. Now, keeping in mind that we don't have to pass everything because we actually have global variables for some of this stuff, right? So x location, y location doesn't really matter. So if we want to skip passing some of these values, the radius, the width, and the color, we can hard code some of that in because we already made sure that we had global variables. However, some things definitely have to get passed. So the current speed has to get passed. The color doesn't have to get passed if we don't want to. Um, let's go ahead and we'll leave that blue. The number 1, again, isn't necessarily needed. We could manually or hard code that in. So we could get by with just passing 2 things in. It really just depends on how you go about defining your programs and whether or not you're globally defining variables such as the X location and Y location and how you want to control those. So it makes the most sense if you're trying to make something that can be configured to define them as global variables. However, if something does need to change, you might want to pass it a different way. So this means that the only things that we're going to be passing in are going to be this current speed. We're going to get rid of all of this other stuff. And if we want to pass in a color, we need to do something called an unsigned int. And we're going to call this color. Then we are starting our new function. So we're going to have the curly braces. And now we can begin basically reusing the code that we've already defined. So what I'm going to do is I'm going to go over to our little program here. We need to have the byte, segment, and increment. We are going to use those. So I am going to put them at the very top of this. And the next thing that we have is this for loop that's iterating through 1 to 99, and it's mapping the speed to that. Now, that isn't needed. We basically spoofed that to pretend like we were sending speed values. But the stuff that is needed is this for loop that allows us to build out those segments. So we need to find where the end of that for loop is. You can see this for loop here is passing the fake speed. This one here is going to be everything we need to actually define the gauge. Keeping in mind that some of these variables aren't going to be right, and we'll need to do a little bit of work there. So let's go ahead and pass this in. I'm going to backspace the for loop. And now we can start to think about what these values actually are. J is perfectly fine, but keep in mind that this arc map value is actually going to be our current speed. So it's going to be our current speed, which we're passing in right here. And then it's going to be the segment. And then we're going to multiply that value by 1. So if we were to pass that random value for segment count, this is where it would come into play, because essentially what it's saying is we would be building out this many segments or this many iterations of this. Because we're not passing it, I'm going to just leave it out, but just note that's where that would go. And then we're going to do plus equals inc. So this is all the same stuff we passed. Where we need to be careful though is that we're no longer passing in X location and Y location into this. We need to make sure that they are defined globally, which they are, because that's how we did it in our sample. So again, it sort of helps us because we use the same values, gauge rad and gauge width, X loc, Y loc, and J is how we're defining this for loop. So that already brings in all of those values. So this should work just fine. The only change that I'm going to make in here is instead of blue, I'm going to say color. And the reason I want to do this is because this helps me define the color of the gauge elements. One way that we could handle this differently is at the very top, we could define things like sweep color, border color, text color, and instead of actually manually passing those in, we could allow those to be configured as well. So if you happen to be, let's say, defining some buttons to be able to change the color, then you would want to define those globally so that you could change them easily. For this example, it's not really going to make that much of a difference, but just so you understand how you can pass the color rather than hard coding it in. So theoretically, this should work, and it should take the current speed from the GPS as well as whatever color we passed into this and build out the gauge to whatever that speed is. Now the trick here is that we are not moving, right? So in order to test this, you actually have to go out and be moving. Now if you're walking a couple miles an hour, you should see something. One way that you can sort of fake that is instead of sweeping or mapping to 270, the entire sweep, what you could do is say that your max speed is 5. So then if you walk 2 or 3 miles an hour, well, you're halfway up the gauge at 270 degrees. So that's a way that you can sort of do some testing. And actually, it's a good way for us to sort of spoof this. So I'm going to set the max at 3 because I know just on my desk I can move the sensor around, and that'll allow me to test to see if it's working. So I haven't saved this yet, which is kind of crazy. So let's go ahead and make sure that we save it. So we're going to call this lead GPS Speedo. All right. So now that we have that, I'm going to go ahead and try to upload it, which will verify it at the same time. And hopefully, because we copied and pasted from a couple other working programs, everything is fine. But there still is the chance that we did forget something. So not great video, but we can see that 1 mile an hour went a quarter of the way up the gauge. And that's because set the max speed at 3 miles an hour. So if we set this back to 100 or 120 or whatever you need, then that's going to configure how far up the gauge, or how many degrees it's going to sweep for the max speed. So that is the basic gauge. I mean, that's pretty much it. It's done. Now, obviously, you can spend as much time as you want configuring what happens, but the basic process is for us to do our global variables at the beginning, so we can define things like the minimum and the maximum speed. Those are going to be used for mapping the values. We have our LCD width and height, which are used to define our X and Y location of our gauge. Also remember that because we've defined this, we can set that XY location wherever we want. But keep in mind, if we do make it smaller, we should think about reducing the text size of the speed in the center and all those different things. We have our gauge delay, which is sort of a universal delay if we want to use it. Then we go into our setup where we're basically beginning the M5 as well as the battery so that we can use it not tethered to a computer. We are starting our software serial communication, and we're telling it that pin 16 and 17 are receiving and transmitting our UART GPS signal. And then we're filling the screen black to just sort of start with a blank canvas. In our loop that happens over and over again is where we have our software serial, and we're looking at whether or not it's available. And if it is, then we're reading the GPS. And once we read the GPS, we say our last speed is equal to our current speed. We pause the program just a little bit, and then we refill in the variable for current speed with whatever the current GPS speed is. This delay can be removed, but you might find that you get a lot of variation if you don't have some sort of delay in there. But again, it doesn't really have to be in there. We could shorten it to 25 or 50 or whatever we want. And all we're essentially doing is we're slowing down the time between capturing the last speed and the current speed. Because remember, this GPS and most are pulling 10 times a second. So we're getting constant stream of updates. So if we pause for half a second or an eighth of a second or a quarter second, then we're essentially filtering out a good chunk of those values because we're just not receiving them, because we're not actually sending a signal to the GPS satellite and pulling whatever data is coming back. Then what we're doing inside of here is we're calling arc with speed. Now, arc with speed is passing two variables, our current speed and the last speed. The arc with speed is really only to condition the variables and to draw the gauge and to draw the arc. So when we draw the gauge, we're passing the current speed, which came directly from the GPS. And then we also pass through last speed just in case we wanted to do some additional programming in here. It's not needed, but it does help us if we want to do some if-else conditioning. From here, after we draw the gauge, we then take our current speed and map it to our min and max values. This is where we change that value to 3, so we could see 1 mile an hour would cover 90 degrees in our gauge. It's mapping it from 0 to 270. If you only wanted the gauge to go halfway around, you would set that to 180. Then we're drawing the gauge, which is blanking it out, drawing a couple 2-pixel wide circles, putting the text in the center, passing the speed value, and displaying miles per hour underneath. Inside of the arc sweep, what we're doing is we're just simply drawing the arcs. Pretty straightforward. Now, you'll notice that in our sample program, we iterated back through 99 down to 0. Well, we don't have to do that in reality because we're passing the current speed. And anytime we pass the current speed, what's happening is everything else is getting wiped out by the draw gauge. So draw gauge is erasing everything on the screen. It's redrawing the red lines and it's redrawing the text. And then we're going into arc sweep and we're filling in that blue section. So we never have to actually go back and go backwards and re-wipe out the gauge because each time we're wiping the whole thing out and we're redrawing it. The thing that is interesting in here is the minus 270 inside of this SX and SY variable. Now, the reason that's there is 1, because we're sweeping 270 degrees, and 2, because we're ending at the 0 position, which is the 3 o'clock position on the clock. And if you wanted that to end at a different location, that's where you need to play around with this mapping number, 0 to 270, and your starting point. So if you want to start, let's say at the 9 o'clock position, that's going to be minus 180. If you want to start at the 12 o'clock position, it would be minus 90. And then you sort of use these to determine how far you want to sweep. That can be a pretty cool trick if you say want to have a speedo on 1/4 of the circle and maybe an air fuel meter or a tach or altimeter or a compass or something else, then you can just configure how much you want that to sweep. But you can see there's really not all that much code here. If we decided to just go with a line instead of filling it in, then we wouldn't need this for loop here. All we would need to do is calculate x1, x2, y1, and y2 and just draw a line between them. So that means that we don't need any of this. We don't need the fill triangles. We just need a line, and we don't even need this loop. We just draw the line. Now, it's only a single pixel line, so you have to decide if you want to try to draw a couple lines and make them thicker or whatever you need to do. But for the most part, it was pretty straightforward. Most of the code is actually in the draw gauge section because that's the most that we're passing over to be drawn. But the next step for this, as I mentioned, would be to configure some more variables. If you include buttons, if you want to change the color, or maybe the button would change between this arc sweep to just a needle to just a triangle. Those are all things that you can do with the M5Stack and with any other microcontroller, but you just need to have all of the little bits and pieces set up for it. If you had any problems with this, please let me know. I know this was fairly large, fairly long anyways, but there's a lot to unpack on a project like this. Even though the code is fairly simple, there's a lot of different steps. So hopefully if at least one person found this helpful. But if you have any questions along the way, please let me know. If there's any more you'd like to see with Arduino and this kind of stuff, please let me know that as well. And if you did actually get to a result, if you were able to make something, feel free to send me some screenshots at support@caducator.com. I'd love to see them and see what you guys decided to make. So as always, thanks for watching, and we'll see you in the next one.